Hello there, and welcome to Physics with William, where curious minds are invited to slow down for a little while, and where even the strangest corners of science are given enough room to breathe. Tonight we're stepping into one of those corners that sounds almost too odd to be real, the kind of idea that arrives dressed like a tabloid headline, and then quietly opens the door to some of the deepest questions in modern physics. The subject before us is this. CERN may have found a particle that seems to change when you look at it. Now, I should say right away, that is the sort of sentence that can make a person sit up in bed a little straighter. It has everything a dramatic headline wants: a giant laboratory, a mysterious particle, a suggestion that reality itself is doing something theatrical. And tucked inside it, perhaps most irresistible of all, is the old unsettling possibility that the universe behaves one way when nobody is paying attention, and another way the moment attention arrives. It sounds like the setup for a ghost story told in a science museum after closing time. It sounds like the sort of thing that ought to come with flickering lights, a locked metal door, and at least one physicist whispering that they do not like where this is going. But before we chase the headline too quickly, let me ask you something simple. Where are you listening from tonight? Or this morning? Or perhaps in some tired little pocket of afternoon where your day is not quite finished with you yet? Are you under a blanket? Are you in a quiet room with a lamp on low? Are you listening through headphones while the rest of the house has gone still? And what is the hour where you are right now? It feels fitting somehow to ask that at the start of a story like this. After all, we're about to talk about particles, measurements, detectors, quantum states, and the peculiar way the world seems to hold itself together. But before any of that, there is still your room, your breathing, your own small location in the universe, and the fact that from wherever you are, you have arrived here at exactly this moment. If this kind of slow scientific wandering is your sort of thing, if you enjoy the strange made gentle and the difficult made clear enough to rest beside, then I would be very glad if you liked the video and subscribed. It helps this quiet little corner reach other people who may want something thoughtful at the end of the day, or perhaps something curious at the beginning of one. And if you find yourself soothed by quantum physics, which is not a sentence people say every day, then you may be exactly where you belong. So let us settle into this carefully, because the question is not really whether a particle has stage fright. It is not whether nature performs differently because a human pair of eyes has entered the room. The real story is at once more subtle and more astonishing than that. It is about what it means to observe anything at the smallest scales. It is about how the act of measuring is never as passive as it sounds. It is about the uneasy boundary between what a quantum system may be doing before we check, and what it is allowed to be once the world has forced it to answer. There is something almost mischievous about the way quantum physics enters ordinary language. Words that seem harmless enough in daily life begin to behave strangely the moment they are brought near atoms and particles. Looking is one of those words, so is measuring, so is state. Even something as innocent as change becomes slippery. In the everyday world, to look at something usually means to gather information, while leaving the thing itself more or less alone. You look at a tree and the tree does not mind. You look at a cup on a table, and the cup does not become nervous about your intentions. If you glance at the moon does not rearrange itself because it has noticed your interest. Our common sense is built on the idea that the world is just there, stable and waiting, carrying on in the same way whether or not we happen to check in on it. At the quantum scale, that simple arrangement begins to wobble. It is not that particles are vain. It is not that electrons prefer privacy. It is not that quarks are somehow aware of being watched and decide to put on a different expression for the detector. The trouble is more mechanical than mystical, though no less strange for that. To find out what a tiny quantum object is doing, you must let something interact with it. You do not merely ask it a polite question from across the room. You prod it with light, collide it with something else, let it pass through a field, catch the traces it leaves, or read the signals it sends into an instrument. In other words, the very process of learning about the system becomes part of the system. That sounds manageable at first, even reasonable. Of course, measurement involves interaction. How else could it work? But quantum theory takes that ordinary fact and gives it extraordinary consequences. It suggests that before a measurement, some systems are not hiding a single neat answer, the way a coin under your hand is hiding heads or tails. Instead, they may exist in a condition where several outcomes are still meaningfully in play, not because we are ignorant in the usual sense, but because the system itself is described that way. A particle can be in a superposition, spread across possibilities that only harden into one definite result when an interaction picks an answer out of the crowd. This is where the dramatic headline draws its power. A particle that changes when you look at it. That is not a good scientific sentence if taken literally, and yet it points toward a real difficulty. When we measure a quantum system, the measurement matters, the apparatus matters, the environment matters, even the difference between isolation and contact matters. Tiny systems can preserve delicate quantum behaviour only so long as the rest of the world does not bully them into acting ordinary. And the world, I'm afraid, is a terrible bully when it comes to quantum delicacy. It is noisy, it jostles, it leaks information everywhere. It turns subtle possibilities into definite outcomes with the casual efficiency of someone closing too many browser tabs at once. One of the reasons stories like this travel so far is that they seem to promise more than physics. They seem to hint at consciousness, intention, mind over matter, and all the old human wishes to be more central to the universe than we probably are. There is a peculiar comfort in imagining that reality waits for us, that it holds its breath until someone notices. It flatters us. It places human awareness near the centre of an otherwise vast and indifferent cosmos. But the science, stubborn as ever, tends to be less flattering and more interesting. Quantum systems do not need a person staring at them. They need only an interaction capable of leaving a mark. A detector will do. A surrounding environment will do. Another particle will do. A random bump from the outside world will do just fine. And yet, despite that clarification, the mystery does not disappear. If anything, it sharpens. Because now the question is no longer whether consciousness has magical powers over matter. The question is how the world moves from possibility to fact. How does a quantum state that can be described in terms of several potential outcomes give rise to one actual event in a detector? How do linked particles carry correlations so deep that measuring one helps define the other, even when they're treated as separate objects? How can certain particles blur the line between one identity and another, behaving in ways that force us to admit that matter at the smallest scales is not only stranger than we expected, but stranger than our everyday grammar was built to handle? Headlines love to make science sound like a miracle or a scandal. Quietly, patiently, actual physics usually turns out to be neither. It is not scandalized by its own weirdness. It does not gasp. It does not perform music cues. It simply keeps presenting results that, when translated into plain language, sound as though they should belong to fiction. Entanglement, for example, sounds like something a novelist would invent after too much coffee and not enough sleep. Superposition sounds like a term from philosophy, rather than something researchers must seriously wrestle with in laboratories. Decoherence sounds bureaucratic, almost dull, until you realize it describes one of the essential reasons the everyday world appears stable and classical instead of forever dissolving into quantum ambiguity. Tonight, the road ahead will take us through all of these. We will talk about what people mean when they say a system is in more than one state at once, and why that phrase is both useful and dangerous. We will talk about particles produced in enormous machines and tracked with exquisite care. We will talk about linked states, fragile behaviours, matter and antimatter, and the way a surrounding environment can wash out quantum patterns that would otherwise remain sharp and strange. Along the way, we will ask what CERN has really found, what it has not found, and why the truth is more satisfying than the myth. Still, at the beginning, I think it is helpful to stay with the headline itself for a little longer, because it reveals something about us as much as it does about physics. we are naturally suspicious of anything that changes when observed. We associate it with shyness, deception, performance, maybe even embarrassment. If a person changes the moment you enter the room, you assume they were doing something else before you arrived. If a child suddenly becomes quiet when you come around the corner, you do not usually congratulate them on their discipline. You wonder what has just been hidden. The same instinct sneaks into our reading of quantum stories. If a particle changes when measured, then perhaps it was doing something secret until the detector spoiled the game. There is a grain of usefulness in that picture and a mountain of confusion built on top of it. The usefulness is this: measurement really does change the situation. The confusion is imagining that the particle was always a tiny classical object with one tidy set of properties, merely waiting to be caught in the act. Quantum theory invites a different view. What exists before measurement may not be a single hidden classical story at all. It may be a genuine quantum state whose possible outcomes are not just unknown to us, but not yet settled in the ordinary sense we would like. That difference is the source of endless headaches, philosophical arguments, scientific progress, and many earnest videos with titles dramatic enough to make a teacup tremble on its saucer. Of course, CERN is exactly the sort of place where such headlines flourish. The name itself carries a certain power. It sounds large, secretive, underground, and faintly cinematic. In truth, much of what happens there is less like cinema and more like the most sophisticated and determined act of bookkeeping humanity has ever attempted. Researchers accelerate particles to extraordinary energies, bring them together, and sort through the aftermath with machines designed to capture patterns so tiny and brief that the rest of us can barely imagine what it means to say they happened at all. It is a place where nature is not bullied into surrendering her secrets, but very carefully cornered into leaving fingerprints. And once in a while, those fingerprints point toward the genuinely profound. Not because someone opened a door and found a glowing object humming ominously in the dark. More often, it's because a pattern in the data suggests that quantum behavior has survived under conditions where it might have been expected to disappear, or because a set of correlations appears with precisely the shape theory predicted for entangled states, or because a particle species turns out to reveal some unstable balance between identities that, in our everyday world, we treat as fixed and separate. Nothing about that is theatrical in the laboratory. It becomes theatrical only when translated for the rest of us, because language has to work hard to carry ideas this peculiar. Perhaps that is why soft exaggerations creep in, changes when you look at it, acts differently when observed, exists in two states at once, communicates instantly with its partner. Each of these phrases is trying to smuggle a difficult truth through customs in a suitcase marked ordinary words. Some make it through with only minor damage, others arrive missing crucial pieces. The result is a public imagination full of half-remembered marvels, where particles respond to thoughts, cats are forever in existential trouble, and the universe appears to be one long misunderstanding between mathematics and English. Yet I would not want to sand away all the drama, because some of it is deserved. Quantum physics truly does unsettle the old picture of reality. It tells us that certainty is not always available in advance, that isolation is precious and easily lost, that correlation can run deeper than common sense expects, and that the line between a system and its surroundings is often where the most important action takes place. These are not minor corrections to a comfortable worldview. They are revisions of the sort that make ordinary life look solid, not because it is simple, but because countless delicate quantum possibilities have already been forced into robust classical outcomes long before we notice anything at all. In a way, that is one of the quiet wonders hiding inside this topic. The world of tables, coffee mugs, train schedules, missed alarms, door handles, raincoats, and unread emails feels stable because immense numbers of microscopic processes have already settled matters on our behalf. We do not wake each morning to find the kitchen existing in a meaningful blur of alternatives. We do not have to measure our toothbrush into one possible state before using it. The reason the world seems dependable is not that quantum strangeness failed, it is that at larger scales, interaction with the environment is so relentless that the strangeness becomes buried under an avalanche of ordinary certainty. Reality is not less weird than the headline suggests. In many ways it is more weird, but also more disciplined. And this brings us, slowly and I hope comfortably, to the heart of tonight's journey. We're not really asking whether a human gaze reaches out like a magic wand and commands particles to become something new. We're asking what quantum systems are like before a definite outcome is recorded. We're asking what measurement means when measuring is a physical event and not just a passive glance. We're asking how entangled states preserve shared information, how certain particles can blur familiar distinctions, and how the surrounding world steadily strips away fragile quantum possibilities until something solid remains. That is the real story behind the dramatic phrasing. The headline says the particle changes when you look at it. The deeper question is how reality changes when anything in the universe becomes capable of finding out. So as we continue, keep that difference in mind. Not the romance of the human stare, but the fact of interaction. Not the idea that particles care about being watched, but the fact that quantum systems can be altered, selected, or forced into definite outcomes by the very processes that reveal them. That small shift in wording turns a misleading mystery into a genuine one, and genuine mysteries, unlike the louder kind, tend to improve the longer you sit with them. Because the first strange thing we have to untangle is the word looking itself, and once that begins to come apart, the whole story starts to look very different. So let us stay with that headline for a little longer, because it is exactly the sort of sentence that sounds impressive before it sounds clear. Did CERN really find a particle that reacts to observation? Did researchers at the Large Hadron Collider uncover some tiny object that behaves one way in private and another way the moment a scientist pays attention? Did they discover a piece of matter that seems to notice the difference between being left alone and being checked on? It is a wonderful headline, and like many wonderful headlines, it is standing with one foot in truth and the other in a puddle. The short answer is no, not in the simple way those words suggest. CERN did not announce that a particle literally senses a human gaze and changes its behaviour like a shy animal in the woods. What CERN has reported, in several very real and very serious results, is something both more technical and more interesting. Researchers have observed quantum entanglement between top quarks at the Large Hadron Collider. They have studied neutral mesons such as the D0 meson, which can exist in a quantum mixture of particle and antiparticle states, and they have described in antimatter experiments how delicate quantum behaviour can be washed out when the system interacts with its surroundings through a process called decoherence. In every case, the important idea is not human watching, it is physical interaction. It is what happens when a quantum system is measured, probed, coupled to a detector, or allowed to leak information into the surrounding world. That distinction matters more than it may first seem. In ordinary life, looking feels passive. You look at a chair, and the chair remains a chair. You look at a loaf of bread, and unless you are having a particularly bad week, it does not become something else, because it felt observed. We carry that intuition with us into science. We imagine observation as a kind of distant inspection, a neutral glance that simply collects whatever is already there. At the quantum scale, that picture starts to break down. To observe something very small, you cannot remain completely detached from it. You need a process that extracts information. That process may involve light, collision products, electromagnetic traps, sensor readouts, or some other physical coupling. The system is not merely revealed, it is engaged. This is where public language often begins to wobble. Someone says a particle changes when observed, and many listeners hear something almost psychological. They imagine awareness, attention, maybe even intention. A less misleading way to put it would be this. Some quantum systems do not settle into one definite measurable outcome until they interact with a measuring arrangement, and the interaction itself helps determine what outcome can actually be recorded. That sentence is less catchy. It would fit very poorly on a thumbnail. Nobody is going to click on a video titled Subtle Issues in Quantum State Selection under Measurement and Environmental Coupling unless they are already exactly the sort of person who alphabetizes T. But the less catchy version is much closer to the real thing. Part of the trouble is that quantum theory forces us to use ordinary words for very unordinary situations. Reaction makes it sound like a tiny personality. Observation makes it sound like eyes. Change makes it sound like the system had one secret condition and then swapped to another when caught. Yet quantum mechanics often asks us to entertain a stranger possibility. Before a measurement, the system may not be hiding one fully settled classical answer at all. It may be in a state that genuinely allows for several possible outcomes to be described together. That does not mean every popular summary gets the details right, but it does mean the world at small scales resists the clean classical script we're used to. CERN, of course, is almost built for these misunderstandings. It is a place with giant machines, underground tunnels, rare particles, huge collaborations, and measurements so refined that the rest of us can hardly picture what is being tracked. Add the words quantum and antimatter, and people start to suspect that reality itself is being held together with dramatic pauses. It does not help that some of the true statements coming out of CERN already sound like they were written to unsettle your evening tea. Top quarks showing quantum entanglement at extremely high energies, a neutral meson existing in a superposition that lets it oscillate into its antiparticle and back, quantum coherence in antimatter experiments being preserved or suppressed depending on how isolated the system remains. These are all real scientific ideas, but once they are translated into everyday language, they can quickly pick up more drama than precision. Take the top quark result, for example. In late 2024, CERN described how the Atlas collaboration had observed quantum entanglement at the Large Hadron Collider for the first time between top quarks and their antimatter counterparts, top antiquarks, using proton collisions from the second run of the collider. The point was not that the quarks changed because someone looked at them. The point was that their quantum properties were linked in a way that could be inferred from the angular patterns of their decay products. The entanglement was not a theatrical reaction to attention. It was a measurable quantum correlation embedded in the system from the moment those particles were produced. And that is a useful example because entanglement is perhaps the most commonly dramatized idea in all of quantum physics. Two particles become linked, people hear that, and immediately the room fills with speculation. Are they communicating? Are they aware of one another? Are they choosing matching answers in secret? What the experiments show is more disciplined and more subtle. The particles are described by a shared quantum state. Their measurable properties are correlated in a way that cannot be understood, as if each one had simply been handed a private little instruction card in advance. When CERN reported entanglement between top quarks, it was showing that even in the violent high-energy setting of collider physics, these quantum links remain physically meaningful and experimentally accessible. That is a major result, but it's not the same as finding a particle that reacts to being watched. Something similar happens with the D0 meson. This is another case where the plain language version can drift into nonsense if left unattended too long. A neutral D0 meson can oscillate into its antiparticle and back, and CERN has described this behaviour in terms of quantum superposition. In a careful explanation, the D0 and the anti-D0 are not best thought of as two little labelled pebbles with a simple swap button. The physically relevant states are quantum mixtures related to lighter and heavier combinations, and that is what allows the oscillation behaviour to exist. A dramatic headline might say the particle cannot decide what it is until looked at. A better sentence would say that the system is governed by quantum rules in which particle identity can involve superposed states that evolve over time and are only pinned down in specific ways by measurement. It is longer, yes. It is also much less likely to make a physicist stare out of a window in defeat. There is a useful habit that can save us from a great deal of confusion here. Whenever you hear that a particle changes when observed, replace the word observed with physically interacted with by something capable of carrying information away. It is not elegant, but it is helpful. A detector counts. A field can count. A trap can count. A collision can count. The surrounding environment can count. Once information about a fragile quantum state leaks into the wider world, the state can no longer behave as though it were perfectly isolated. That loss of delicate quantum behavior is not magic. It is one of the central facts of how the everyday world emerges from the microscopic one. This is why decoherence is such an important part of the story, even though the word itself sounds like it should belong to an office policy memo. CERN has described in antimatter work how interactions with the surrounding environment can quickly suppress interference effects through quantum decoherence. In plain terms, if you want to preserve a delicate quantum state, you must keep the system from chatting too freely with everything around it. The environment is dreadful gossip. It steals information and spreads it everywhere. Once that happens, the system loses the kind of coherent quantum behavior that made it interesting in the first place. Again, nothing here requires a conscious observer. The environment does the job perfectly well all by itself. There is something almost disappointing about that if you arrived hoping for a cosmic drama centered on human attention. No special privilege for the scientist with the clipboard. No mysterious influence of the eyeball. No particle sitting there waiting to decide what it wants to be only when a person leans in. Yet the real picture is hardly dull. In some ways it is far more unsettling. It tells us that reality at the smaller scales is not neatly divided into systems that simply possess all their classical properties all the time in the way our daily objects seem to. It tells us that isolation and interaction are not minor side issues, but central ingredients. It tells us that what can be said about a system depends not only on the system itself, but also on how it is prepared, what it becomes coupled to, and what kind of information becomes available to the rest of the world. You can see why the headline writer gets tempted. If a system behaves one way when left alone, and another once it becomes entangled with a measuring device or surrounding environment, then change when you look does not feel entirely unfair as a cartoon version. The trouble is that cartoons flatten the machinery that makes the result meaningful. They skip over the role of apparatus. They skip over the difference between a superposition and ordinary ignorance. They skip over the fact that the detector is not just passively reading out a pre-written answer. They skip over the way entanglement can spread from one system to another. They skip over the hard experimental work required to infer these effects from particle decays, trapped antiprotons and collision data. The phrase survives because it is vivid. The science deserves better because it is real. There is also a second misunderstanding hidden inside the headline, and it is one that comes from our own instincts more than from physics. We tend to think that if measurement matters, then surely the system must have been different before we measured it, in the same simple way a sealed envelope contains a letter before we open it. Classical thinking trains us to imagine hidden facts waiting patiently behind a curtain. Quantum theory does not always let us keep that picture. In some cases, it is not just that we do not know which outcome will appear. The full description of the system before measurement may simply not assign a single, definite value in the classical way we would like. That is a difficult idea to handle, because our everyday language was built for tables and weather and grocery lists, not for superposed states of neutral mesons and entangled top quark pairs. At this point, it helps to remember that CERN itself is not claiming anything mystical. The collaborations involved are careful. They talk about statistical significance, decay products, spin correlations, transition spectroscopy, mixing, oscillation, coherence, environmental effects. They are not declaring that particles become self-conscious when placed under professional scrutiny. The strangeness enters when these results leave the papers and begin their life in the open air of the internet, where every subtlety is asked to wear brighter clothes. Then suddenly, a result about quantum entanglement in high-energy collisions becomes proof that reality responds to being watched. and a result about superposition becomes a story about a particle changing its mind. One might be tempted to laugh that off as harmless exaggeration, but there is a reason it keeps happening. The real science presses directly on one of the oldest assumptions we have, which is that the world is made of things with definite properties that exist in the same stable way whether or not anything interacts with them. Quantum physics does not completely destroy that assumption in every context, but it does fence it in. It tells us there are domains where the very idea of a property must be treated with more care. It tells us that the act of making a measurement cannot always be pictured as lifting a curtain on an already finished play. Sometimes the measurement is part of the event that turns a range of quantum possibilities into a specific recorded outcome. And that is why CERN did not find a particle that reacts to observation, but it did help reinforce something stranger. It reinforced that nature at the smallest scales is not obliged to respect our comforting separation between what is there and how we ask about it. The top quark entanglement result matters because it shows quantum correlations surviving and being measurable in a setting of astonishing energy and complexity. The D0 meson story matters because it reminds us that particle identity can involve superposed behaviour rather than the simple labels our intuition prefers. The antimatter coherence work matters because it shows how fragile quantum behaviour can be when the surrounding world is allowed to meddle. These are not separate curiosities. Together they point toward a picture in which measurement, interaction, and environment are woven into the description from the start. It is worth pausing on one especially common phrase because it turns up everywhere in popular summaries. The particle changes when you look at it. Even now, after all our caution, I can feel why people say it. There is a compact honesty buried inside the bad wording. Something about the experimental setup really does matter. Something about the process of obtaining a result really does shape what result can appear. Something about isolation really does preserve a richer quantum description than the one that survives once the system has been allowed to interact too widely. So the sentence is not wrong because it notices change. It is wrong because it smuggles in the wrong cause. The crucial cause is not human-looking. It is measurement as a physical process. That may sound like a dry correction, but it is actually the doorway to the entire subject. Once you stop imagining a particle performing for an audience and start thinking about detectors, interactions, state preparation, information leakage, and the emergence of definite outcomes, the mystery becomes much more serious. It stops being a cute paradox for posters and becomes a deep question about what the quantum description is really telling us. Are measured properties created, selected, revealed, or stabilized by the measurement process? How should we think about superposition before a result is recorded? What does it mean for an entangled system to yield definite local outcomes while preserving shared global structure? Why does the world of large objects feel so stable if its ingredients obey rules this slippery? These are the questions hiding under the headline, and I think they are much better company than the headline itself. The headline is loud for a moment and then tires you out. The real question lingers. It asks you to imagine that the difference between a private quantum system and a measured one is not a minor inconvenience, but one of the main clues to how reality is stitched together. It asks you to accept that a detector is not just a notebook with wires attached. It is part of the physics. It asks you to abandon the fantasy that looking can always be cleanly separated from touching. So no, CERN did not discover a particle that reacts to observation, in the sense of reacting to a person looking at it. But yes, CERN has been at the centre of experiments and results that show how quantum systems can behave in ways that make observation itself a physically consequential idea. That is a more demanding thought and a more honest one. And before we can make sense of superposition, entanglement, or why a detector matters at all, we need to slow down even further and ask what physicists actually mean by looking in the first place. So when physicists use the word looking, they're usually not talking about eyes, attention, or anything as human and ordinary as staring at something from across the room. They're talking about a process by which information about a quantum system becomes tied to something else in the world. That something else might be a detector, a screen, a magnetic trap, a surrounding field, a nearby particle, or a larger environment full of restless degrees of freedom. In quantum physics, looking means arranging things so that the system leaves a record. And once a record can exist, the situation is no longer the same as it was before. Measurements are the bridge between quantum states and classical readouts, and extracting that classical information generally changes or destroys part of the original quantum state in the process. That sounds more technical than the headline version, but it is also the cleanest way to understand what is going on. If I say a particle changes when you look at it, your mind naturally supplies the wrong image. You picture a scientist peering over a bench, perhaps squinting nobly through a screen, while the particle somehow senses that it has become the centre of professional interest. Real measurements are not like that. A measurement is a physical event. It is not a thought. It is not a mood. It is not a human gaze wandering into the room. It is some arrangement in which the quantum system becomes correlated with something larger that can carry away information about it. Once that happens, the delicate rules governing an isolated quantum system are no longer all you need to describe what follows. In the everyday world, we do not usually notice how much this depends on scale. Looking often seems passive because our objects are large, stable, and already thoroughly entangled with their surroundings. If you glance at a chair, you do not imagine that your act of seeing has changed the chair in any meaningful way. Light bounces off it, enters your eyes, and that is that. But even there, in a very plain sense, information still had to travel. The object had to interact with light. The light had to interact with your retina. Your nervous system had to turn that into a visual experience. It only feels passive because the chair is not a fragile quantum system, balancing on a knife edge of coherence. It is a loud, warm, macroscopic object that has already spent every moment of its existence interacting with air, thermal radiation, vibrations, and the rest of the room. By the time you see it, the quantum subtlety has long since been beaten flat into ordinary certainty. At very small scales, by contrast, the difference between isolation and interaction becomes the whole story. A well-isolated system can preserve the kind of coherent quantum behavior that allows interference, superposition, and entanglement to remain physically meaningful. Let it interact too strongly with a detector or the environment, and that coherence is reduced or lost. CERN made exactly this point in its discussion of recent antimatter work. The laboratory described how quantum interference effects can be quickly suppressed by surrounding interactions through decoherence, and why preserving coherence is essential when researchers want to control and track the evolution of a single antiproton in a trap. There is a simple way to feel the difference, even if the details remain unfamiliar. Imagine trying to learn whether a bubble drifting through the air is intact without disturbing it. At human scales, you could perhaps shine a very gentle light on it and trust that the bubble is sturdy enough for the test. Now imagine the bubble is not sturdy at all. Imagine the smallest touch, the faintest gust, the tiniest contact with the outside world is enough to change its behavior. Suddenly, checking and disturbing become hard to separate. That is closer to the quantum situation. The system is not being precious. It is simply operating under rules where information and interaction are linked far more tightly than common sense would prefer. This is why the double-slit experiment remains so famous, not because it is the only strange result in quantum mechanics, but because it makes the role of looking almost impossible to ignore. Send particles through two slits without determining which path each particle took, and over time the detection screen builds up an interference pattern. Try to obtain which path information, however, and the interference pattern disappears. The important point is not that a human being must consciously inspect the data. The NIST analysis of measurement-induced decoherence phrases it very clearly. Interference appears when no attempt is made to determine which path the particles took, and it disappears when a detection setup acquires that information. In other words, gaining path information prevents interference from showing itself in the same way. That is a useful place to pause, because it is easy to hear the phrase which path information and still import too much ordinary intuition into it. In daily life, information feels abstract. It sits in a notebook, on a hard drive, in a memory, on a shopping list. In quantum physics, information is physical from the start. For a system to carry information about another system, the two must become linked in some measurable way. A detector that can tell whether a particle passed left or right is not just standing politely nearby. It has entered the physics. It has become part of the overall description. That is why measurement cannot be treated as a final decorative step, something added after the real story is over. It is often one of the events that determines what kind of story the system is allowed to tell. People sometimes try to simplify this by saying that the measurement apparatus just knocks the particle around. There is some truth in that image, but it can be too crude if left on its own. A measurement is not always best pictured as one tiny billiard ball slamming into another and ruining the shot. Often the more important idea is that the system becomes correlated with the apparatus. The apparatus is arranged so that different possible properties of the system get tied to different readable outcomes. Once those correlations spread into a large environment, the weirdly quantum parts of the description become inaccessible in practice, and what remains is a definite record. That is one reason the transition from quantum possibility to classical outcome still feels so conceptually sharp. It is not merely a bump. It is an information-making event. You can see this in the language used by quantum computing researchers as well. IBM describes measurement as the interface between quantum and classical information. That is a very dry phrase, and a very good one. A system begins in a quantum state. A measurement extracts classical information from that state. In the process, the state is generally changed or destroyed in the form it had before the measurement. If you say that slowly enough, you can almost hear how different it is from the everyday meaning of looking. We are not just peeking at a thing. We are converting part of a quantum description into a classical record. That conversion is not free. This is also why consciousness is such a distraction in discussions like these. It keeps wandering into the conversation because the word observer sounds as though a person must sit at the centre of the story. But the essential physics does not wait for a mind. A cloud chamber does not need to feel curious. A detector array does not need an opinion. A magnetic trap does not need a philosophy degree. If the apparatus becomes correlated with the system, and the information is amplified into a stable record, then the physics of measurement is already in motion. Human awareness may arrive much later, when someone reads the instrument output over coffee and wonders why their fit did not converge the first time. There is a quiet relief in that, I think. The universe is strange enough without requiring our eyeballs to serve as magical operators. No evidence from the CERN results we've been discussing suggests that particles care whether a person is watching. The top quark entanglement measurements at the Large Hadron Collider relied on the angular patterns of decay products recorded in detectors. The particles were not waiting for applause. Their quantum relationship was inferred from the readout of the experiment. Likewise, in the antimatter work at CERN, preserving spin coherence in a trapped antiproton depended on suppressing environmental disturbances and measurement interference, not on shielding the antiproton from human curiosity. It helps to separate three ideas that often get bundled together under the single word looking. The first is probing the system. The second is allowing information about the system to become stored in another physical system. The third is producing a stable macroscopic record that the larger world can in principle access. In ordinary language, all three get compressed into the idea that we looked. In quantum physics, those steps matter. A very weak interaction may disturb the system only slightly. A carefully designed measurement may reveal one property while leaving another uncertain. A strong, well-amplified readout may destroy coherence so thoroughly that the earlier quantum alternatives can no longer interfere in any accessible way. Looking is not one thing, it is a family of physical processes. This is one reason experiments can be so subtle. Physicists are not always asking a system one blunt question. Sometimes they want to preserve coherence while extracting a little information. Sometimes they want to isolate the system for as long as possible so that a fragile quantum effect can survive. Sometimes they want to force a clean readout at the end and do not mind sacrificing the earlier state. The apparatus is built accordingly. The geometry matters, the timing matters, the noise matters, the coupling strength matters, the background magnetic field matters, temperature matters, vacuum quality matters. Looking, in the laboratory sense, is engineering. Now, if all this sounds as though quantum measurement is simply ordinary measurement made more inconvenient, not quite. There is a deeper issue here that people often sense even before they can name it. In daily life, we assume that the thing we are measuring already has the value we are about to read. You check the temperature of the soup because you believe the soup already has a definite temperature, whether or not you happen to own a thermometer. At the quantum level, the situation is more delicate. The theory does not always license the same casual assumption that all measurable properties sit there in advance, with fixed classical values waiting to be revealed one by one. This is where measurement ceases to be just a practical nuisance and becomes a conceptual fault line. That fault line is easy to miss if we speak too casually. Suppose I say that measuring a quantum system changes it. You might hear only an everyday disturbance. You may think of checking the pressure in a tyre and letting out a bit of air in the process. That is a good analogy up to a point. It captures the basic idea that the act of checking is not perfectly innocent, but it does not yet capture the full quantum problem because it still assumes that the system had a complete set of classical properties before you checked. Quantum mechanics pushes harder than that. It suggests that certain properties are not all jointly available in the way classical intuition expects, and that the measurement context helps decide which definite outcomes can emerge as classical facts. This is why the difference between an unmeasured quantum system and a measured one can feel so dramatic. Before a strong measurement, the system may be described in a way that still contains multiple possible outcomes as part of a single coherent state. After measurement, you do not get a beautifully coherent mixture continuing onward in everyday life. You get a record, a click in a detector, a flash in a sensor, a counted event, a spin read as one outcome rather than another. The path from one description to the other is where much of the philosophical tension lives, even though laboratory physicists are usually too busy making the apparatus behave to spend every afternoon arguing about metaphysics. And yet the metaphysics keeps knocking, because the lab results refuse to stay neatly in their boxes. If which path information destroys interference, we want to know why. If entanglement creates correlations stronger than classical intuition allows, we want to know what that says about the measured properties of each part. If coherence can be preserved in one setup and lost in another, we want to know what exactly has changed. These are not empty questions. They shape how experiments are designed and how results are interpreted. They also shape how careful we need to be when translating the science into ordinary language. So when someone says that looking at a quantum system changes it, the best response is not to laugh, and not to surrender to mysticism either. The best response is to ask what kind of looking they mean. Do they mean a weak interaction, or a strong one? Do they mean path information in an interference experiment? Do they mean a detector becoming entangled with the system? Do they mean environmental decoherence washing out a fragile state? Do they mean a final recorded outcome in a classical instrument? These are all real physical situations, but they are not interchangeable, and too many popular accounts toss them into one bag and shake. The better picture is calmer and more exact. A quantum system can remain in a delicate coherent state only while the relevant information about its alternatives has not been irreversibly spread into the wider world. Once a measurement setup or environment becomes capable of carrying that information away, This system no longer behaves as though those alternatives can interfere in the same clean way. This is why experimentalists work so hard either to isolate a quantum system or to read it out decisively depending on the aim. Isolation protects possibilities. Measurement turns some of those possibilities into outcomes, and this is where the road naturally bends toward the next question. If looking in quantum physics really means interaction, information, correlation, and readout, then what exactly is it that exists before that readout becomes definite? What kind of state is being protected during isolation and altered by measurement? What does it mean to say that several outcomes are somehow present in the description before one of them is finally recorded? To answer that, we need to sit with one of the most abused and most important ideas in all of modern physics, which is superposition. One of the reasons people get tangled so quickly in quantum physics is that the ordinary word seems simple, right up until the moment they stop being simple. Superposition is one of those words. It sounds manageable. It sounds like something can be stacked, layered, or added together. Then someone tells you that a particle in superposition can be more than one thing at once, and suddenly the whole conversation starts leaning toward either science fiction or complete despair. One person hears that and imagines a particle literally split into multiple tiny versions of itself, each one doing its own little errand. Another hears it and decides the physicists have lost the plot entirely. A third reaches for a cat, a box, and a headache. And somewhere in the middle of all this, the actual idea sits there waiting to be described properly. So let us take it slowly, because superposition is not nonsense, but it is also not captured well by the first dramatic sentence most people hear. When physicists say a quantum system can be in a superposition, they mean that the full state of the system can include multiple possible outcomes in a single coherent description before a measurement picks out one definite recorded result. That sounds abstract because it is abstract, but it is not empty. It has real consequences. It predicts interference effects. It changes how probabilities must be calculated. It shapes what can be measured together and what cannot. And it has been tested so often and so carefully that the question is no longer whether superposition is useful. The question is how to talk about it without making it sound either trivial or magical. The most tempting mistake is to translate superposition directly into everyday language as a particle being several ordinary things at once, in the way a person might be a teacher, a cyclist, and hungry all at once. That is not the right picture. Quantum alternatives are not like a list of classical labels all simultaneously attached in the usual sense. They are components of a single quantum state that can evolve together and interfere with one another until a measurement arrangement forces definite outcome into the open. The word coherence matters here. A superposition is not just a messy pile of options. It is a structured, phase-related quantum state. Lose that coherence, and the strange behaviour that made the superposition meaningful in the first place is lost with it. That is why so much of quantum research depends on protecting delicate systems from outside disturbances long enough for their coherent behaviour to matter. An ordinary analogy can help up to a point. Imagine a melody played on a violin. Before the sound reaches you, it is not best described as one note after another locked in separate boxes. The richness of the sound comes from a structured combination of vibrations. If you destroy that structure, you do not get a deeper truth about the melody. You just get noise. Superposition is not the same as music, of course, but the analogy helps with one point. The parts are not merely sitting side by side like groceries on a shelf. They belong to a single state whose structure matters. Measurement, then, is not like calmly reading a label off a shelf. It is more like forcing the system to answer in a particular basis, to use the physicist's phrase, and in doing so turning a richer quantum description into one definite kind of classical outcome. This is why the old question, does a particle really become more than one thing at once, is both understandable and slightly off target. The best answer is that the particle is described by a quantum state that cannot always be reduced to a single ordinary classical condition before measurement. That may not sound as thrilling, but it is far more precise. The particle is not playing dress-up. It is not indecisive. It is not switching back and forth too quickly for you to catch it. Nor is it secretly one thing all along in the same simple way. A card face down on the table is secretly a queen or a 7. The superposition is not merely our ignorance in the everyday sense. It is part of the physical description itself. That distinction between a hidden classical answer and a genuine superposition is one of the hardest things to make peace with, because our intuitions are trained on bigger objects. If I tell you that a coin under my hand has not yet been revealed, you assume it is already either heads or tails. The uncertainty belongs to you, not the coin. Quantum theory does not always let you keep that tidy division. A spin state, a path through an interferometer, a polarization, an oscillating neutral meson. These are not always well described as simply having one fixed classical value before measurement and merely waiting for us to catch up. Sometimes the system behaves in ways that show the alternatives must be treated together as parts of a coherent state. Interference is the clue, correlation patterns are the clue. The mathematics is the formal tool, but the experiments are what stop this from being just an elegant philosophical headache. This is where the subject begins to touch your CERN theme more directly. One of the real examples that gives people the dramatic sense of a particle being more than one thing at once comes from neutral mesons. CERN has described how neutral D0 mesons can oscillate into their antiparticle counterparts, and the explanation involves superposed quantum states rather than a simple picture of a tiny object wearing one fixed identity badge at all times. The physical states that propagate are quantum mixtures related to lighter and heavier combinations, and because of that, the system can evolve in a way that lets a D0 become an anti-D0 and back again over time. That does not mean the meson is indecisive in a human way. It means the clean classical distinction between particle and antiparticle is not the only language the quantum state allows. This is one of those cases where the popular phrasing is both misleading and useful. If someone says the meson is both particle and antiparticle at once, a physicist will begin reaching for careful qualifications. And yet the sentence survives because it points toward a real feature of the theory. The state is not best thought of as one little nugget of matter sitting quietly in a single classical category. It is described by a superposition of possibilities that evolve coherently. When the conditions are right, that coherence produces behaviour which would make no sense if the meson had simply been carrying a fixed ordinary label all along. The dramatic sentence is not the science, but it is leaning in the direction of the science. This is also why superposition cannot be separated from measurement. People often want to know what a particle really is before we look. That seems like a plain question, perhaps the plainest question possible. Yet quantum theory answers it in a way that resists ordinary grammar. Before measurement, what the system is may be exactly the superposed state, not one secretly settled classical answer hiding behind the curtain. Then the measurement setup matters because it determines what kind of answer can become definite in the readout. Ask about one property in one way and you get one kind of outcome. Arrange a different measurement and the same prior state may yield a different set of possible outcomes. That is not because the particle is being difficult. It is because quantum states are richer than the ordinary list of classical properties we wish they would hand over. The double-slit experiment still offers one of the clearest ways to feel this. If particles were simply tiny pellets that went through one slit or the other in the ordinary classical sense, then over time the distribution on the screen would look like a mixture of two simple patterns. But when which path information is not obtained, the pattern instead carries interference. That interference is the fingerprint of a superposition of paths. It tells you that the alternatives must be treated together as parts of one coherent quantum description. Once you arrange things so that which path information can be acquired, the interference disappears. The system no longer behaves as though those alternatives remain coherently combined in the same way. That is one reason superposition sounds strange. It is not just a verbal trick. It produces different observable consequences depending on whether coherence is preserved. A useful way to state it, though one that must be handled gently, is this. A superposition is not a list of things the system is secretly taking turns being. It is a state in which several measurable possibilities remain physically linked in a way that can affect later outcomes. That last part matters. If all you had were ignorance about a classical hidden answer, the probabilities would combine one way. In a coherent superposition, they combine differently, and the difference shows up in real experiments. That is why physicists take the concept so seriously. It earns its keep. Now, the phrase more than one thing at once will continue to bother some listeners, and fairly enough. It feels grammatically rebellious. In the everyday world, identity is expected to be tidy. A light is either on or off. A door is open or shut. A train has either arrived or it has not, though some rail systems do try to explore more creative interpretations. Quantum systems do not always share our affection for clean binaries, or perhaps better said, the full description of the system before measurement does not reduce neatly to one of the classical alternatives. What is definite in the quantum description is the state itself. What becomes definite in the classical sense is the recorded outcome once the measurement interaction is complete. This is where many people either become fascinated or mildly annoyed. They want the theory to tell them what the particle was doing all along in the same tone one might use to ask who ate the last biscuit. But quantum physics keeps turning the question around. It tells you how to describe the state, how it evolves, what measurement statistics to expect, what interference patterns can appear, what correlations can survive, and what coherence can be lost. If you insist on a small classical object with a full set of ordinary hidden properties at all times, the experiments begin to resist you. The theory is not refusing to answer out of spite. It is telling you that the question, as posed in ordinary classical terms, does not fit the structure of the phenomena. The fact that this sounds philosophical should not mislead you into thinking it is merely philosophical. Laboratories depend on it. Quantum technologies depend on it. If coherent superpositions could not be prepared, maintained and manipulated, large parts of modern quantum research would collapse into a pile of expensive disappointment. The difference between a coherent superposition and an ordinary classical mixture is not decorative. It is operational. It decides what patterns appear, what information can be extracted, and what behavior remains possible as the system evolves. That is why decoherence is such a menace. Once the environment starts carrying away information about the alternatives, the carefully maintained superposition stops behaving like a single coherent state and starts looking more like an ordinary mixture of outcomes. That brings us to something else the phrase more than one thing at once gets wrong if left alone. It makes the superposition sound stable and comfortable, as though the particle can simply lounge in several identities indefinitely without consequence. In practice, coherent superpositions are often fragile. They are not impossible, but they are precious. Heat, stray fields, collisions, vibrations, imperfect isolation, even the possibility of information leaking into the surroundings can degrade them. At CERN, this issue appears very directly in antimatter research. The laboratory has described how preserving the coherence of a trapped antiproton spin is essential for precision measurement, and how interactions with the environment lead to decoherence that suppresses the very quantum interference effects researchers wish to study. That is the real world of superposition. Not just weirdness, but a constant struggle to protect that weirdness long enough to learn something from it. It is worth noticing how different this is from the lazy cartoon version of the quantum world. In the cartoon, particles just do impossible things because quantum physics is whimsical. In the real science, superposition is a disciplined concept with strict rules, measurable signatures, and delicate dependencies. You do not simply declare that something is in two states and call it a day. You prepare the state, you control the couplings, you track the evolution. You choose a measurement basis, you analyze the outcome statistics, You fight noise and drift and environmental leakage. The strangeness remains, but it is a worked strangeness, a tested strangeness, not a decorative one. And yet, even with all that discipline, the conceptual shock does not entirely fade. There is still something profoundly unsettling in the idea that a system can be described in a way that includes several alternatives together until interaction forces a definite classical record. It unsettles our sense that reality should always come pre-packaged in complete ordinary facts. It unsettles the belief that uncertainty is always just ignorance. It unsettles the habit of thinking that the world has a single finished script before the measurement begins. Superposition does not destroy reality. It complicates what we mean by reality before the outcome is fixed. This is one reason neutral mesons are so useful as examples. They show that superposition is not just a classroom party trick involving simplified two-state systems. At CERN and elsewhere, the behavior of mesons has made it clear that quantum mixtures of particle and antiparticle states are not philosophical toys. They are part of real particle physics, with measurable consequences such as oscillation and tiny mass differences between relevant states. The D0 meson story is compelling precisely because it sounds like a contradiction in ordinary language while remaining entirely sensible in the quantum framework. The meson is not literally half deciding which passport to carry. The state itself is built from a superposed structure that the experiment can probe. There is another mistake people sometimes make when first meeting superposition, and that is to imagine that all alternatives in the superposition are equally real in the same practical sense all the time. Quantum theory is subtler than that. The state may assign different weights to different outcomes, and the measurement context decides how those possibilities become relevant. In one setup, the superposition may reveal itself through interference. In another, it may appear only through the statistics of repeated measurements. In yet another, the surrounding environment may destroy the coherence before the strikingly quantum features ever become visible. So more than one thing at once is not a magical badge the particle wears under all circumstances. It is a shorthand for a state whose structure matters, whose coherence matters, and whose measurable consequences depend on how the system is handled. The more carefully you look at superposition, the more you realize it sits at the center of the entire mystery. Without it, the quantum world would be odd perhaps, but not truly unsettling. With it, measurement becomes a live problem. Entanglement becomes possible. Interference becomes meaningful. Decoherence becomes decisive. The everyday classical world begins to look less like the obvious default and more like the large-scale consequence of countless delicate superpositions being constantly interrupted, monitored, and washed into stability by their environments. What seems ordinary may in fact be what quantum strangeness looks like after it has been forced into silence. So when a headline tells you that a particle can be more than one thing at once, the best response is not immediate belief and not immediate dismissal. The best response is to ask what kind of state is being described, what measurement outcomes are possible, what interference or oscillation or correlation reveals the superposition, and how well the system is being isolated from the environment. Those are the questions that turn a sensational phrase into physics. They also prepare us for the next turn in the story, because once you accept that a particle can exist in a coherent state involving multiple possibilities, the obvious next question is what happens when two particles stop being describable as separate tidy things at all, and instead share a state together. That is where superposition stops being a solitary oddity and begins to weave itself into something even more unsettling, which is entanglement. There is a special kind of discomfort that arrives when physics tells you a particle is not content to keep one identity card in its pocket. We are used to matter and antimatter being introduced as opposites, neat reflections, the sort of pair you can arrange on a blackboard and feel you have done something orderly. This particle is matter, that one is antimatter. They have matching masses, opposite charges where charge applies, and if they meet under the right conditions they may destroy each other in a burst of energy. It feels tidy. It feels like the sort of distinction nature ought to respect at all times, and then along comes the D0 meson, which takes that tidy distinction, looks at it with mild disinterest and begins to blur it. At CERN, the D0 meson is described as a particle that can oscillate into its antimatter counterpart, the anti-D0, and the reason it can do that is that the physically relevant quantum states are superpositions rather than one permanently fixed classical label. So let us meet this particle properly. The D0 meson is made of a charm quark and an up antiquark. Its antimatter counterpart, the anti-D0, is made of a charm antiquark and an up quark. On paper, that sounds clear enough. One is matter, the other antimatter. One carries one combination of quark content, the other the mirror-swapped version. If all you wanted was a pair of names and ingredients, the story could end there. But the D0 is not interesting because of what it looks like in a diagram. It is interesting because nature does not leave it frozen in that diagram. The D0 belongs to a small family of neutral mesons, whose quantum behaviour allows them to turn into their antiparticles and back again. CERN describes this as oscillation, and it is one of the reasons the D0 has become such an important laboratory for studying the strange borderland between matter and antimatter. If you hear that too quickly, it can sound as though the particle is simply flipping back and forth like a sign on a shop door. Matter now, antimatter later, matter again after lunch. But that picture is too mechanical and not quantum enough. The deeper story is that the D0 and the anti-D0 are not the most fundamental way to describe how the system propagates through time. CERN explains that the D0 can be itself and its antiparticle at once in a quantum superposition, and that this superposition produces two states with slightly different masses, a lighter one and a heavier one. Those two states are commonly referred to as D1 and D2. It is the tiny mass difference between those superposed states that controls the speed of the oscillation between D0 and anti-D0. So the particle is not best imagined as changing its mind. It is better imagined as being governed by a quantum description in which the clean everyday boundary between one identity and the other is not the whole story. That's why I find the D0 meson such a useful guide through this landscape. It takes the slippery idea of superposition and gives it a physical body, however brief that body may be. The D0 particles produced at the Large Hadron Collider do not hang around for leisurely philosophical inspection. CERN notes that they travel only a few millimeters on average before decaying into other particles. They are fleeting, unstable, and gone almost as soon as they appear, and yet in that short lifetime they leave enough trace for physicists to study how their identity evolves. By comparing D0 mesons that decay after shorter and longer travel distances, the LHCb collaboration was able to measure the tiny mass difference that controls the oscillation. This was reported by CERN in 2021 as a milestone result, and it crossed the 5 sigma threshold used in particle physics to claim an observation. There is something wonderfully rude about that. A particle exists only for a moment, moves barely farther than the width of a grain of sand, and still manages to force humanity into a discussion about whether matter and antimatter are really as separate as our schoolbook instincts would prefer. The D0 does not live long, but it makes good use of its time. It shows us that the quantum world does not have much respect for the tidy labels that comfort us at larger scales. In the classical imagination, identity is solid. A coin is a coin, a spoon is a spoon. An object is not halfway into being its opposite unless something has gone badly wrong with the furniture. But in the quantum description of the D0 system, the matter label and the antimatter label do not sit alone on separate islands. They are linked through superposition and oscillation, and the system evolves in a way that makes those labels part of a larger structure, rather than final declarations. This is also a good place to be careful, because the phrase suspended between matter and antimatter can be beautiful and also slightly treacherous. It may sound as though the D0 spends its life in a vague metaphysical fog, unable to commit to either camp. That is not quite right. The quantum description is not indecision. It is not hesitation. It is not a particle suffering an identity crisis in an underground tunnel outside Geneva. The superposed states are precise parts of the theory, and they have measurable consequences. The oscillation rate is tied to a real mass difference. The decay patterns can be counted. The statistical significance can be tested. This is one of the great themes of quantum physics. The language sounds dreamy until the data arrive, and then the dream turns out to have left fingerprints on every instrument in the room. CERN also linked the D0 system to a second major subject, which is matter-antimatter asymmetry. In 2019, CERN announced that the LHCb collaboration had observed what is known as charge parity violation, or CP violation, in D0 meson decays for the first time. The D0 meson and the anti-D0 were studied through their decays into kaons or pions, and the collaboration found a small but statistically significant difference in behaviour between the particle and antiparticle decays. This mattered because CP violation had previously been observed in particles containing strange or bottom quarks, but the D0 result was the first evidence of this asymmetry in a system involving the charm quark. CERN described it as a milestone in the history of particle physics, and noted that understanding CP violation is essential because the amount seen so far in the standard model is not enough to explain the observed dominance of matter over antimatter in the universe. Now that point deserves a slower landing. The D0 meson is not just a strange little system because it oscillates. It is also valuable because it gives physicists another place to test whether matter and antimatter really behave as exact mirror images under all circumstances. If they did, the universe would look one way. If they do not, even by a tiny amount, then some cracks appear in the symmetry, and those cracks may be clues to one of the oldest questions in cosmology. Why is there so much matter around us now when the early universe is thought to have produced matter and antimatter in equal amounts? CERN is careful here. The observed CP violation in known standard model processes is too small to account for the full imbalance we see today. But every new system where this asymmetry can be studied matters, because each one tests whether the existing theory is complete or whether something more is waiting in the wings. This gives the D0 meson an unusual personality in the story of modern physics. It is not the loudest particle. It does not have the celebrity status of the Higgs boson. It does not carry the familiar romance of antimatter atoms trapped for long precision studies. It appears, oscillates, decays, and vanishes. And yet it stands at the crossroads of several of the most serious ideas in particle physics. It is a charm particle. It is a neutral meson. It can mix with its antiparticle. Its behaviour is governed by superposed states with slightly different masses. Its decays can reveal tiny symmetry violations between matter and antimatter. It is, in short, a small particle carrying very large questions. There is another reason this matters for your broader topic about particles seeming to change when looked at. The D0 system reminds us that quantum weirdness is not always about measurement, forcing a result in the narrow sense. Sometimes the weirdness is already present in the way the state is constructed and evolves. Even before a detector records the decay products, the D0 and anti-D0 labels are not enough by themselves to capture the full physics. The system has to be described through superposition. That matters because it pushes back against the comforting classical story in which a particle always carries one complete definite identity all the way through until a measurement simply reveals it. The D0 meson suggests that the world is under no obligation to package itself in those terms. Sometimes the right description is inherently quantum from the start. That does not mean anything goes. Quantum theory is not a poetic license for saying contradictory things with a knowing expression. The D0 is not both matter and antimatter in every casual sense you might invent over tea. The point is more disciplined than that. There are specific states, specific mass differences, specific decay channels, specific observables, and specific experimental signatures. LHCb measured the tiny mass difference by comparing particles that decayed at different effective times. LHCb measured the matter-antimatter asymmetry by counting decay outcomes into kaons and pions over a large dataset gathered between 2011 and 2018. These are not vague claims about reality being mysterious. They are hard-won results from a collaboration built to notice very small departures from very demanding expectations, and still, despite all that rigour, the conceptual strangeness survives intact. The D0 meson can begin its life produced as one flavour, if we may borrow the particle physicist's language, and yet the actual states that govern its propagation are quantum combinations of matter and antimatter versions. Because those combinations have slightly different masses, their relative evolution changes with time, and that changing relative evolution is what allows the observable oscillation between D0 and anti-D0. The strange thing is not just that the particle changes, it is that the most faithful description already contains the seeds of both identities in a linked quantum structure. Nature is not writing one label on the box and then crossing it out later. It is using a deeper grammar from the beginning. One of the quiet lessons here is that antimatter is not always best approached as the theatrical opposite of ordinary matter, though it certainly has theatrical moments. At CERN, antimatter research also includes antihydrogen, trapped antiprotons, and extreme efforts to isolate these systems from normal matter so they do not annihilate on contact. CERN notes that any contact between a particle and its antiparticle leads to immediate annihilation, which is why antimatter must be stored in very high vacuum and electromagnetic traps. That practical fact makes antimatter sound like an exotic guest who absolutely must not be allowed near the furniture. But the D0 meson offers a different view. Here matter and antimatter are not kept apart as separate objects in a trap. They're entangled in the quantum identity of a neutral meson system itself. It is a less explosive image, and, in some ways, a more unsettling one. If you step back from the details for a moment, the D0 meson becomes almost a miniature summary of what the quantum world keeps trying to teach us. First, that definite everyday labels can be emergent conveniences rather than universal truths. Second, that superposition is not a decorative oddity but a working part of how particle systems behave. Third, that tiny measurable effects, such as a minuscule mass difference or a very small asymmetry in decay rates, can carry enormous conceptual weight. And fourth, that the line between matter and antimatter, while real and physically important, can enter the dynamics of a quantum system in ways far subtler than a simple mirror image story would suggest. I think that is why the D0 meson lingers in the mind more than its brief life might seem to warrant. It is not because it is flashy, it is because it quietly refuses to let the universe be as simple as our first pass at language would like. It asks us to imagine a particle whose existence is bound up with a superposition of matter and antimatter states. It asks us to accept that oscillation can be the natural consequence of that structure. It asks us to consider that the search for why the universe favours matter may need to inspect these tiny shifting systems with immense care. And it does all this while living only for a moment and leaving the rest to decay, products, statistics, and the patience of large collaborations. By now, perhaps, the phrase suspended between matter and antimatter no longer sounds like a cheap exaggeration. It sounds more like an imperfect translation of something precise and hard-earned. The D0 meson is not floating in indecision. It is obeying a quantum rulebook in which the deepest physical states are mixtures, the masses are almost but not quite the same, and the observed identity can evolve as the state moves through time before it decays. That is not merely a curiosity tucked away in a particle table. It is one of the cleanest reminders that the world at very small scales is built from descriptions richer than the blunt categories our senses evolved to trust. And once you are willing to accept that one particle can carry a quantum identity broader than a single classical label, the next step becomes hard to avoid. If one particle can be described through superposed possibilities that only later show themselves in definite outcomes, then what happens when two particles are born in a shared state and carry that connection with them? What happens when the puzzle is no longer one system hovering between matter and antimatter, but two systems whose properties are linked in a way that resists being broken into separate local stories? That is where the road bends from oscillation to entanglement, and from one strange particle to a pair of them. By the time we arrive at entanglement, quantum physics has usually already loosened the screws of common sense a little. We have accepted that measurement is not passive. We have accepted that superposition means a system can be described in a way that does not fit the tidy classical story we prefer. We have even made room for the possibility that a particle can sit in a quantum relation to its own antimatter counterpart. Even so, entanglement has a way of making all of that feel like the warm-up act. It takes the strange behaviour of one system and extends it across two. It says that under the right conditions, two particles are not best described as separate little things, carrying separate little private stories. They are described by a shared state, and that shared state can leave measurable traces that neither particle, taken alone in a classical way, can fully explain. At CERN, this moved from abstract principle to collider fact, when the Atlas and CMS collaborations observed quantum entanglement between a top quark and a top antiquark produced at the Large Hadron Collider. That result matters for several reasons at once. The first is simply scale. Entanglement had already been studied in many systems before, but CERN described the top quark observation as the first at the Large Hadron Collider and the highest energy yet. The second is the particle itself. The top quark is the heaviest known fundamental particle, which already makes it unusual company. The third is timing. Top quarks decay extremely quickly before they have time to combine with other quarks, and in doing so they pass their spin information and other quantum traits to their decay products. That means physicists cannot hold a top quark in place and ask it polite questions. They must infer its quantum properties from the spray of other particles that appears almost immediately after it's produced. This is not an easy system in which to study delicate quantum ideas, which is precisely why the result is so striking. There is a temptation, whenever entanglement is mentioned, to turn it into a kind of secret messaging service. Two particles share a hidden link. One is measured here, the other somehow knows there. That language has dramatic value, but it also requires care. CERN describes entanglement as a situation in which the state of one particle is tied to the state of the other, no matter how far apart the particles are. What this means in practice is not that a signal is being sent back and forth in the ordinary sense. It means the pair has to be described by a shared quantum state, and when measurements are made, the outcomes show correlations stronger or more structured than a classical account with separate pre-written stories would naturally predict. The link is real, but it is not a tiny courier sprinting between the particles. It is built into the state from the start. That distinction is important because entanglement has suffered from two equal and opposite misunderstandings. One side drains it of all wonder and speaks as if it were merely an awkward bookkeeping trick. The other side pours in so much wonder that it becomes a vague spiritual fog. Neither helps much. In the Collider result, the entanglement was not a metaphor and not a mood. It was inferred from measurable spin correlations in pairs of top quarks and top antiquarks produced in proton collisions. The Atlas and CMS teams used data from the second run of the Large Hadron Collider, collected between 2015 and 2018, at a collision energy of 13 tera-electron volts. They selected events where pairs of top quarks were produced and then examined the patterns in the decay products to reconstruct what the underlying spins had been doing. This is entanglement turned into careful statistical labour. Spin is the thread that holds this part of the story together. One does not need to picture spin as a tiny billiard ball literally rotating. In particle physics, it is a quantum property, and for top quarks it can be transferred to the particles they decay into before the quarks themselves disappear. CERN explains that physicists infer the spin orientation of the top quark by studying the decay products, especially the directions in which electrically charged decay products are emitted, If the top quark and the top antiquark were simply two unrelated objects, those angular distributions would follow one kind of pattern. If they are entangled, the pattern shifts in a specific way. The shared quantum state leaves its mark not by surviving long enough to be admired directly, but by shaping how the wreckage of the event is arranged. It is rather like learning something about a conversation by studying the way two people leave a room. Except here the conversation lasts less than a whisper, and the room is full of detectors the size of buildings. Atlas and CMS both focused first on pairs of top quarks produced with low relative momentum. CERN notes that this is the region where the spins of the two quarks are expected to be strongly entangled. From there, the teams measured the angles between the directions of the charge decay products and corrected for experimental effects that might distort the values. What emerged was not a vague hint, but a statistically significant observation. CERN reported that both collaborations observed spin entanglement with a significance greater than 5 standard deviations, which is the usual threshold particle physics uses to claim an observation rather than a suggestive fluctuation. That matters because entanglement is easy to romanticize and much harder to establish in a violent collider environment, where everything is fast, messy, and short-lived. The signal survived the mess. There is another detail that makes the result especially satisfying. The top quark is not just heavy, it is also unusually honest, at least by particle standards. Because it decays before forming bound states with other quarks, its spin information is passed on before the usual complications of hadron formation can blur the picture too much. In less poetic terms, the top quark's extreme short-lived nature helps preserve information that experimentalists can later extract from the decay products. That does not make the work simple, but it makes the system uniquely useful. A particle that disappears almost immediately turns out to be one of the best places to test whether the quantum link between a pair can survive under the harsh conditions of the Large Hadron Collider. There is something almost unfairly elegant about that. The most fleeting of the heavy particles becomes a window into one of the deepest features of quantum theory. CMS then pushed the story a little farther into territory that sounds almost designed to unsettle the room. In a later study, the collaboration also examined top quark pairs produced with high momentum relative to one another. CERN reports that in this domain, for a large fraction of the pairs, the relative positions and times of the two decays are such that any classical exchange of information by particles travelling no faster than light is excluded. CMS described this in plainer language by noting that the two particles are far enough apart before decaying that their separation exceeds what information travelling at light speed could cover in time. And yet the spin entanglement is still observed. This is the point where the phrase hidden link begins to earn its keep, provided we remember that the hidden part is not a secret signal, but the non-separable structure of the quantum state itself. Einstein once called entanglement spooky action at a distance, and CERN's CMS material freely nods to that famous phrase. It is memorable because it captures the emotional effect the phenomenon has on common sense. Still, it can be misheard. Nothing in the top quark result licenses faster than light communication in the everyday sense. The CMS explanation is careful on this point. The correlations appear even when ordinary information transfer at light speed cannot account for them. But the underlying issue is not that one particle sends a message after the other is measured. The issue is that the pair is born in a joint quantum state, and that shared state constrains the measurement outcomes in ways classical hidden stories struggle to imitate. The weirdness lies less in a forbidden message, and more in the fact that the best description belongs to the pair as a whole. Separate the particles in space, if you like. The state that matters was never merely local in the classical sense. This is one of those moments where language almost gives up. We're used to saying that objects have properties. The apple is red, the chair is wooden, the train is late. Entanglement encourages a different grammar. It asks us to admit that sometimes the pair has a property that neither member of the pair possesses by itself in the same simple way. The top quark here and the top antiquark there are not fully described by separate local fact sheets. What matters is the joint state. That may sound abstract, but the Large Hadron Collider result gives it concrete footing. The shared structure shows up in the angular distributions of the decay products, and those distributions agree with entangled expectations rather than a simpler classical alternative. The pair is not just two things side by side. It is a single quantum story with two endings being written at once. There is also something quietly important about where this happened. Entanglement is often introduced through carefully isolated laboratory systems that seem almost fragile by design. Photons in optical setups, ions and traps, engineered systems shielded from noise as much as possible. The Large Hadron Collider is not usually anyone's first image of delicacy. It is a machine that collides protons at enormous energies and leaves detectors sorting through immense volumes of debris. To observe entanglement, there is to show that quantum correlations are not merely curiosities reserved for gentle tabletop experiments. They survive and can be measured in the rougher, louder domain of high-energy particle physics. CERN explicitly framed the result this way, calling it a new perspective on quantum physics at energy ranges beyond what had previously been accessible. That gives the result a philosophical flavour, yes, but it also gives it practical reach. It means collider physics can now serve as a laboratory for quantum information ideas and foundational tests. That last point should not be passed over too quickly. The top quark entanglement result was not merely a novelty item to be placed in a cabinet labelled very strange and otherwise ignored. CERN quoted both collaborations as emphasising that these measurements open a path to new tests of the standard model and possible searches for new physics. If quantum entanglement can be studied in top quark pairs, then future datasets with more events and improved analyses can probe whether the patterns remain exactly as expected or begin to show deviations. This is one of the most satisfying habits in physics. Even the strangest result is rarely allowed to remain only strange. It is quickly put to work. Entanglement becomes a tool as well as a mystery. A concept that once felt like a philosophical provocation begins doing the practical job of helping test our deepest theories. The hidden link between two top quarks, then, is not hidden because it is occult. It is hidden because it has to be inferred. No detector prints a friendly sentence saying these two were entangled. What the experiment records are tracks, energies, jets, leptons, angles, uncertainties, and enormous amounts of background complexity. The link must be reconstructed from patterns across many events. That is one reason I find the result so appealing. It refuses both the lazy mystical summary and the lazy dismissive one. It is not that the world contains magical invisible threads in the childish sense. It is that the quantum state of a pair can impose structure on what later appears, and careful enough analysis can reveal that structure even in the aftermath of violent proton collisions. The hiddenness lies in our access, not in the absence of the effect. There is another quiet lesson in the choice of top quarks. These particles are part of the third generation of quarks, the heaviest and least stable set in the standard model. All stable matter around us is built from the lightest generation, while heavier particles decay rapidly into more stable products. In that sense, top quarks are visitors from a deeper layer of the theory, not the building blocks of your table lamp or your teacup. And yet even these brief, unstable visitors obey the quantum logic of entanglement. That should perhaps make the phenomenon feel less exotic, not more. Entanglement is not an oddity that happens only in rare, polished systems. It is woven into the logic of quantum theory broadly enough to show itself in the behaviour of the heaviest known fundamental particle and its antimatter partner at the largest collider on Earth. You can also feel in this result a gentle correction to the old headline about particles changing when you look at them. The top quark story is not chiefly about a single particle being forced into an answer by measurement. It is about a pair being born with a shared quantum structure that later measurements can uncover. The detector does not create the entanglement out of thin air. The detector reveals it through the decay patterns. That matters because it broadens the whole conversation. Quantum weirdness is not only about measurement collapsing possibilities, it is also about systems whose properties are relational from the start. Two particles can carry a link deeper than any classical handshake, and that link does not wait for human attention to become real. It is already there in the state long before the analysts begin arguing with the data selection and the machine learning models. And yes, there was machine learning involved as well, because nature apparently enjoys layering modern complications onto old philosophical puzzles. CMS notes that state-of-the-art machine learning methods were used to assign decay products correctly, and improve the modelling of systematic uncertainties in the high-speed top quark study. That detail is easy to overlook, but it says something about the kind of science this is. Entanglement at the collider is not an idea floating alone in a thought experiment. It is a measurable pattern, extracted with sophisticated statistical and computational methods from a mountain of imperfect real-world data. One can still marvel at the idea, but one should marvel just as much at the craftsmanship required to see it clearly in the first place. Quantum foundations, it turns out, now sometimes arrive with calibration files and training pipelines. The emotional centre of the result, though, remains older and simpler than any algorithm. Two particles are created together. They rush apart. They decay before any ordinary signal could shuttle between them in the time available. And still the measured outcomes bear the signature of a shared quantum state. It is hard not to feel, at least for a moment, that reality is leaning just slightly away from the comfortable picture we inherited from larger objects and slower lives. The world at its foundation is not always built from separate things carrying separate truths. Sometimes it is built from wholes that only later pretend, under measurement and distance, to be ordinary parts. Entanglement is not the end of logic. It is a reminder that logic had more room in it than common sense first allowed. That is perhaps why the top quark result feels so important beyond the technical details. It shows that the hidden link of entanglement is not confined to fragile low-energy systems. It survives at the frontier of collider physics. It appears in the behaviour of particles so short-lived that they never settle into the composite states many other quarks form. It can be inferred from the patterns left by their decays, tested against stringent statistical standards, and used as a fresh handle on the standard model itself. The story sounds dramatic because it is dramatic, but the drama has earned its place. Two of the heaviest particles we know can share a quantum connection that outlives every classical excuse we might try to give it. And once you have accepted that, another question begins to wait just around the corner. If superposition tells us how one system can carry several possibilities together, and entanglement shows how two systems can share a state that resists being split into separate classical stories, then what actually turns those delicate possibilities and shared links into the stable, ordinary world we experience? Why do chairs not appear entangled with nearby tables in ways that ruin breakfast? Why do large objects not walk around advertising their superpositions? Somewhere between the collider and the kitchen, something is constantly smoothing over the quantum richness into everyday certainty. That smoothing has a name, and it is where the story next becomes less flashy, more merciless, and in some ways even more important. What a measurement really does is one of those questions that sounds as though it ought to have a short answer and then refuses to behave. In ordinary life, measurement feels almost boring. You step on a scale, read a number, and assume the number was already there waiting for you. You check the temperature of the room, and you do not imagine that the thermometer has forced the air into becoming that temperature. You glance at the clock, and you do not suspect that time itself had been wandering around undecided until your eyes arrived. The whole classical world teaches us to think of measurement as a reveal. The facts already exist in their finished form. The instrument simply peels back the curtain. Quantum physics is difficult partly because it does not always let us keep that comforting arrangement. It tells us that measurement is the interface between quantum and classical information, and that when a measurement is performed, classical information is extracted from the quantum state while the state is generally changed or destroyed in the process. That sentence may sound dry, but it is far more radical than it first appears. Measurement is not just note-taking. It is not a harmless glance. It is the physical process by which the sprawling, delicate, possibility-rich description of a quantum system is forced into the kind of definite outcome that a detector can record. Before that outcome appears, the system may be described by a superposition, a coherent combination of possibilities that can interfere and evolve together. After the measurement, you no longer have that same unmeasured state. You have a result, a click, a mark, a flash, a spin read one way rather than another. The experiment has not merely learned something, it has participated in the event that produced the learnable fact. IBM states this very plainly. Measurement extracts classical information from quantum states and generally changes or destroys the original state in the process. This is where many people begin to feel that the floor has shifted under them, because common sense keeps trying to smuggle the old picture back in. It whispers that surely the particle had one correct answer all along, and measurement just happened to uncover it. Sometimes that classical instinct works well enough for practical talk, but quantum experiments keep revealing cases where it is not the full story. If a system were merely hiding a pre-written classical answer, then the patterns seen in interference experiments would not look the way they do. The double-slit experiment remains the cleanest example. NIST describes it as the classic example of both interference and the effect of observation. When particles are sent one by one through two slits, without obtaining which path information, a wave-like interference pattern develops. When one observes which path the particles take, that interference is lost. NIST further explains that the loss of interference is correlated with the information gained by the measuring apparatus or observer. In other words, the acquisition of path information is not a side note. It is tied directly to the disappearance of the delicate pattern that only a coherent superposition can produce. That is why measurement has to be understood as a physical interaction, and not merely as human attention. The word looking is too gentle for what is really happening. In order to get information out of a quantum system, you need some apparatus, some coupling, some physical arrangement that lets the system leave a trace in the wider world. A screen records where a particle arrived. A detector correlates one possible state with one signal and another possible state with another. A trapped particle interacts with fields and sensors in carefully controlled ways. Once that record can exist, the system is no longer isolated in the same manner. The outside world has gotten involved. This is why the universe does not require a person peering into the apparatus for the measurement to matter. The apparatus itself is enough. The environment itself may be enough. The key is that information about the quantum alternatives has escaped into a larger system that can in principle carry the record forward. There is a useful emotional shift that happens once you start thinking about measurement this way. The question stops being why does the particle care that we are watching, and becomes what kind of interaction is turning a coherent quantum description into a definite classical outcome. That is a better question, because it points toward real laboratory practice. Experimental physicists do not arrange a system so that it can feel observed. They arrange a system so that different possible quantum states become tied to different measurable signals. Then they work ferociously hard to make sure stray interactions do not destroy the coherence too early, or distort the final readout beyond recognition. In a good experiment, measurement is not philosophical hand-waving. It is architecture. It is timing. It is calibration. It is the art of deciding when to protect the quantum state from the world and when to let the world extract an answer from it. The CERN antimatter work gives a very concrete example of this tension. In its report on the base collaboration, CERN described how a single trapped antiproton was kept oscillating coherently between two spin states for almost a minute. CERN also explained that interactions with the surrounding environment can quickly suppress interference effects through quantum decoherence, and that preserving coherence is essential for controlling and tracking the evolution of such quantum systems. Earlier, the relevant transitions had been disturbed by magnetic field fluctuations and measurement interference. Only after those decoherence mechanisms were suppressed could the collaboration achieve coherent spectroscopy of an antiproton spin for a period of 50 seconds. That is measurement in the laboratory sense laid bare. Researchers were not merely asking what state the antiproton happened to be in. They were engineering the conditions under which a coherent state could survive, and only then arranging measurements that could extract useful information without immediately ruining the phenomenon they hoped to study. This helps answer a question people often carry into quantum mechanics without quite naming it. If measurement changes the state, then what exactly was there before the measurement? The safest answer is that before measurement the system is described by its quantum state, and that state may contain multiple possible outcomes in coherent superposition. What measurement does is connect that state to a particular classical basis of outcomes, producing one actual recorded result. That does not automatically settle every philosophical question about what reality is doing underneath. Different interpretations of quantum mechanics tell different stories about how best to picture the transition, but the practical content is stable. The theory tells you how to predict outcome probabilities, how repeated measurements should behave, and how interference and coherence disappear when information about the alternatives becomes available to a measuring arrangement or environment. The mathematics is not in doubt. The discomfort comes from the fact that the world does not seem eager to tell us a simple classical story about what happened before the result was pinned down. This is where people sometimes reach too quickly for the word collapse, which can be useful so long as one remembers it is a description of the transition from an unmeasured quantum state to a definite outcome in the measurement context, not a little physical explosion happening in space. The danger of the word is that it can make the process sound either mystical or mechanical in the wrong way. On one bad day, it sounds like consciousness reaches into the lab and snaps reality into place. On another bad day, it sounds like a hidden classical answer was always there, and the collapse is merely a dramatic way of saying, reveal. The actual laboratory picture is more restrained and more demanding. Measurement couples the system to something larger. Information is extracted. Coherence relative to the measured alternatives is lost or rendered inaccessible. A definite outcome is recorded. Whether one chooses to speak of collapse, branching, updating, or some other language depends on interpretation. What does not depend on interpretation is that the state before the measurement and the state after the measurement are not the same kind of thing. Another way to feel this is to think about how fragile quantum possibilities can be. We often imagine the world waiting calmly to be inspected, but in quantum systems the distinction between waiting and interacting is delicate. If you want to know which path a particle took, you must build an arrangement capable of carrying that information away. But once that information is available, the interference pattern that depended on the paths remaining coherently combined is gone. NIST is explicit that the loss of interference is correlated with information gained by the measuring apparatus. That is the central lesson. A measurement is not just something that happens at the very end when a human reads a display. The possibility of gaining the relevant information already changes what patterns nature is allowed to show. The apparatus does not have to shout. It merely has to know how to listen in the right way. That phrase, the possibility of gaining the information, is quietly devastating to classical intuition. It means that measurement is not always best pictured as a violent shove that batters the system into one answer. Sometimes what matters is that the alternatives become distinguishable in principle by the larger setup. Once the paths, spins, or states are tied to different records in the world, the coherent quantum story no longer survives in the same accessible form. The system has become entangled with the apparatus or environment, and the classical world begins to emerge from that spreading web of records. This is one reason decoherence is such a powerful idea. It explains why large objects do not walk around showing off obvious superpositions. They are continuously interacting with air, light, heat, vibration, and countless surrounding degrees of freedom. Their quantum alternatives are constantly being monitored by the environment whether anyone has taken out a notebook or not. So from possibility to outcome is not a poetic transition. It is the central labour of measurement. A quantum state carries the possibility structure. The The apparatus selects what kind of question is being asked. The interaction correlates different possibilities with different signals. The environment or readout amplifies the result into a stable classical record. What had been a coherent set of alternatives is no longer available in that original form. A measurement has occurred. IBM calls measurements the interface between quantum and classical information because that is exactly what they are. They are the bridge by which the fluid, interference-capable language of quantum states is converted into the blunt certainty of an outcome you can write in a lab book. There is still, of course, a lingering tension here, and it is worth respecting rather than pretending it has vanished. Even once you understand the apparatus, the information flow and the role of decoherence, the mind still wants to ask whether the outcome was somehow already there in secret, or whether the measurement truly played an indispensable role in making it definite. Physics, in its practical mode, answers by giving the rules for predictions and by showing again and again that those rules work. Philosophy continues to worry the bone of what the rules mean. There is nothing shameful in that. The question is deep because the situation is deep. But for our purposes here, the essential point is firm enough. A quantum measurement does not merely uncover a fact from a safe distance. It is the physically structured event through which a quantum state yields a classical result. The cost of that result is usually the loss of the unmeasured state that existed before. And once you begin to see measurement this way, another part of the story starts to clarify. The everyday world looks definite not because quantum possibilities were never there, but because interactions keep turning those possibilities into outcomes at a furious pace. The environment is constantly measuring in a broad physical sense. Light scatters, heat flows, surfaces vibrate, fields fluctuate, information leaks out. The world records itself into itself over and over again until stability becomes the dominant face it shows us. That is why a chair feels so unlike an electron. Not because the chair is exempt from quantum rules, but because it has spent every instant of its existence being forced into robust classical behaviour by its coupling to everything around it. At the smallest scales, physicists struggle to protect coherence long enough to preserve possibility. At human scales, possibility is being pounded into outcome all the time. So if the older headline asked whether CERN found a particle that changes when you look at it, the better question now becomes what happens when measurement turns a quantum possibility into a recorded event. The answer is not that the particle becomes embarrassed. It is that the measuring process extracts classical information from a quantum state and in doing so changes or destroys the very state whose delicacy made the question interesting in the first place. That is the real drama. Not a particle reacting to human attention, but a world in which definite facts emerge only through interactions that also erase some of the richer quantum structure that came before. Once that sinks in, the next step is almost unavoidable, because if measurement and environment keep stripping away coherence, then we need to understand the mechanism that performs that stripping so mercilessly. That mechanism has an unlovely name and an essential role. It is decoherence, and it is the great quiet enforcer that stands between the quantum world and the ordinary one. If superposition is the part of quantum theory that unsettles your instincts, decoherence is the part that explains why your instincts usually survive the day anyway. It is not the most glamorous word in the story. It does not arrive with the drama of entanglement, or the eerie charm of a particle that seems to be more than one thing at once. It sounds administrative, as though someone in a grey office has filed the quantum world under a different heading and moved on. But decoherence is one of the central reasons the world around you feels solid, ordinary and dependable, instead of shimmering with obvious quantum strangeness at every moment. It is the process by which interactions with the surrounding environment suppress interference effects in a quantum system and reduce the visibility of the very coherence that made the system behave in a strikingly quantum way to begin with. CERN states this directly in its antimatter report, noting that interactions with the surrounding environment can quickly suppress interference effects through quantum decoherence. The Stanford Encyclopedia of Philosophy similarly describes decoherence as the study of situations in which interference effects are spontaneously or artificially suppressed by interactions between a system and its environment. There is a quiet brutality to that idea. A quantum system may begin in a delicate coherent state, rich with alternatives that are still able to interfere with one another. Left suitably isolated, those alternatives can remain part of one structured quantum description. But the surrounding world is rarely polite enough to leave such a system alone. Light scatters, air molecules collide, thermal vibrations shake, magnetic fields drift. Nearby particles jostle. Information about the system leaks outward into degrees of freedom that nobody invited into the conversation. Once that leakage begins, the coherent alternatives do not remain available in the same way. The environment effectively begins to monitor the system, not with human intention, not with consciousness, but simply through physical interaction. The result is decoherence. The system starts to lose the phase relationships that allowed its alternatives to interfere cleanly. And with that loss, the strikingly quantum behavior becomes harder or impossible to observe. This is why decoherence matters so much for understanding measurement. It shifts the story away from the childish image of a particle becoming shy when someone looks at it and toward the more serious picture of information spreading into the world. The double-slit experiment remains one of the cleanest ways to feel this. Erosion describes it as the classic example of both interference and the effect of observation in quantum physics. When particles are sent through two slits without obtaining which path information, an interference pattern appears. When the arrangement is such that one can determine which path the particles took, that interference no longer appears in the same way. Erosion's point is not that human attention casts a spell over the apparatus. It is that information gained by the measuring setup is correlated with the loss of interference. That is decoherence in its most famous outfit. The paths stop behaving like one coherent quantum story and start behaving like alternatives whose information has been allowed to leak into the wider world. It helps to notice that decoherence is not a separate decorative theory pasted onto quantum mechanics after the fact. It is what you get when you take quantum mechanics seriously for systems that are not perfectly sealed off from everything else. Real systems are almost never alone. They are coupled, however weakly or strongly, to environments that have immense numbers of degrees of freedom. Even a tiny unwanted interaction may be enough to spoil a fragile quantum effect. The theory of decoherence studies exactly this. The Stanford Encyclopedia describes it as the study of concrete interactions between a system and its environment that lead to suppression of interference, and asks how the classical world may emerge from quantum mechanics. That is an important shift in perspective. Decoherence is not mainly about adding mystery. It is about explaining why mystery becomes hard to see. There is something almost funny about that if you take a step back. Popular accounts of quantum physics often make it sound as though the universe is desperate to behave strangely at all times. In fact, what the theory and the experiment suggest is nearly the opposite. Quantum systems can behave in extraordinarily delicate ways, but the surrounding world is extremely efficient at silencing those delicacies. The environment is less like an audience and more like a very noisy neighbour. It does not need to understand what the system is doing in order to ruin the performance. It merely needs to couple to the system strongly enough that information about the alternatives is dispersed. Once that happens, the interference effects that depended on coherent superposition are washed out. The weirdness has not been disproved. It has been drowned in interaction. This is why preserving coherence is such a prized achievement in modern experiments. Researchers are not only trying to create quantum states, they are trying to keep those states from falling into conversation with the rest of reality too soon. CERN's antimatter work offers a particularly vivid example. In the 2025 report on the base collaboration, CERN explained that the team had managed to keep a single trapped antiproton oscillating coherently between two spin states for 50 seconds. Earlier spectroscopy techniques had been incoherent because quantum transitions were disturbed by magnetic field fluctuations and measurement interference. Only by suppressing and eliminating those decoherence mechanisms could the collaboration achieve coherent spectroscopy of an antiproton spin. CERN called this the first antimatter qubit. That phrase may sound futuristic, but its meaning is grounded in the same struggle found across quantum science. To do anything subtle with a quantum system, you must stop the environment from stealing the coherence before you have had a chance to use it. There is a very human tendency to imagine that the important action happens at the moment of the final measurement. The detector clicks, the number appears, the graph updates. But decoherence teaches a harsher lesson. Much of the important action may have happened long before the final readout, during all the uncontrolled or partly controlled interactions that gradually turned an isolated, coherent state into something more classical. By the time the final detector announces an outcome, the environment may already have done most of the work of selecting which alternatives can still interfere and which have become effectively separate. In that sense, decoherence is often the long, quiet prelude to the definite outcome. It is not always the theatrical moment itself. It is the steady erosion of quantum ambiguity by contact with the rest of the world. A useful way to picture this, without abusing the science too badly, is to imagine writing a message in water on a calm surface. For a moment the shape is there, the structure holds. If the surface stays calm, the message can remain visible long enough to be noticed. But let wind, vibration, and stray droplets disturb the water, and the message blurs into ripples so quickly that its form can no longer be recovered. The message was not false, it was fragile. Decoherence is like that blurring, except the thing being blurred is not a visible line on water, but the phase relationships that allow quantum alternatives to interfere. The environment does not need to hit the system like a hammer. It merely needs to keep touching it in enough small ways that the coherence becomes inaccessible. That is why decoherence can be both relentless and ordinary. It is the sum of countless interactions that each seem modest on their own. This also helps explain one of the most important facts in the whole story. Decoherence does not mean that quantum mechanics stops applying, quite the opposite. Decoherence is a quantum mechanical account of why large systems begin to look classical. The environment and the system become entangled in a huge, complicated way. Because the information about the quantum alternatives has spread into so many surrounding degrees of freedom, those alternatives no longer produce observable interference in the simple local system you are tracking. The state of the small system alone starts to resemble a classical mixture rather than a neatly coherent superposition. That resemblance is enough to make the everyday world look stable and definite. The weirdness has not been banished from the laws. It has been redistributed into correlations that are practically impossible to reverse or observe directly. Now, there is an important subtlety here, and it deserves honesty. Decoherence does a great deal, but many physicists and philosophers do not treat it as a full answer to every measurement question. The Stanford Encyclopedia presents decoherence as highly relevant to the measurement problem and to the emergence of the classical world, but also notes that the relation between decoherence and the full measurement problem is something that needs analysis rather than automatic triumph. From that, it is reasonable to say that decoherence explains why interference is suppressed and why systems begin to appear classical, but it does not by itself settle every interpretive argument about why one definite result is experienced in any given run of an experiment. That is not a weakness of the concept. It is a reminder that the concept is doing a specific job, and a very important one, without necessarily carrying every philosophical burden on its own. Even so, the job it does is immense. Without decoherence, the world of everyday objects would be far harder to understand. Why do chairs stay where they are? Why do planets follow stable paths instead of displaying obvious interference patterns? Why do dust particles not announce themselves as coherent spreads of alternatives? The broad answer is that large systems are never isolated in the way an idealized quantum experiment tries to isolate a microscopic system. They are interacting with their environments all the time, and those interactions constantly suppress the kinds of coherence that would reveal overtly quantum behavior. The world of breakfast tables, lamp switches, train tickets, and folded laundry is not outside quantum mechanics. It is what quantum mechanics looks like after the environment has had its way with nearly everything. This returns us to the Matter-antimatter example, because it shows how hard physicists must work to push back against that everyday tendency. Base was not merely performing a measurement on an antiproton. The collaboration had to suppress magnetic field fluctuations and measurement interference precisely because those effects were causing decoherence. Only after reducing those disturbances could the researchers hold on to spin coherence for 50 seconds. CERN explicitly framed this as preserving coherence being essential for controlling and tracking the evolution of quantum systems, like the transitions between spin states of a single antiproton. That sentence contains the whole battle in miniature. Coherence is what makes the quantum behavior useful and visible. Decoherence is what the surrounding world does to erase it. Experimental skill lies in postponing that erasure. There is also a lesson here about scale and innocence. At human size, we rarely notice that our interactions with things are destructive to delicate quantum structure, because the systems around us are already so deeply decohered. Looking at a chair does not seem to alter it, because the chair has long since lost any coherent superposition that would have made such alteration interesting in the first place. It is already bathed in thermal radiation, jolted by molecular collisions, lit by scattered photons, and embedded in an environment that records its state over and over again. By the time you see it, the chair is less like a lonely quantum system and more like a public announcement. The world has already measured it for you 1,000,000 times. That is why the classical world feels so easy. It is not because the quantum world beneath it is simple. It is because the environment has been doing relentless cleanup work all along. The phrase silences quantum weirdness is therefore useful so long as we treat it carefully. Decoherence does not silence quantum theory itself. It silences the observable interference and coherent structure that make a system look overtly quantum. The laws remain quantum. The larger combined state of system plus environment remains within the theory. What disappears, for all practical purposes, is the ability of a local observer to see the alternatives interfere as a single delicate whole. The quantum weirdness goes quiet, not because it has been proven unreal, but because it has been spread into so many environmental correlations that recovering it becomes fantastically difficult. It is less like the weirdness has died, and more like it has been diluted into the entire room. And there is something almost tragic about how ordinary this process is. The universe does not wait for a grand act of measurement to crush coherence. Countless tiny interactions do the work continuously. A stray photon can matter. A slight fluctuation in a magnetic field can matter. A bit of unwanted thermal contact can matter. That is why quantum technologies are so demanding. It is not enough to know the principles. One must wage a constant practical war against decoherence. The more delicate the superposition, the more merciless the environment appears. IBM's broad overview of quantum computing puts it bluntly in engineering terms. Decoherence is the process in which a quantum state becomes non-quantum through measurement or environmental factors, and avoiding or minimizing decoherence is essential in quantum computing. That is not a poetic summary, but it captures the central practical truth. Quantum systems are powerful because of coherence. They are difficult because coherence is hard to keep. In a way, decoherence is the missing middle term in the whole conversation we have been having. Superposition tells us a system can carry several possibilities together. Measurement tells us a definite outcome can be extracted. Decoherence tells us how the surrounding world steadily pushes systems from the first condition towards something that behaves like the second, often long before a formal laboratory readout arrives. It is the process by which the environment begins to keep score. Once the environment has learned too much, the delicate game of coherent alternatives is effectively over. The system starts to look classical, not because nature changed the rules, but because those rules, applied to a system plus a vast environment, no longer leave the local quantum weirdness visible in the same way. So when people say the quantum world is strange but the ordinary world is not, I think they're only half right. The ordinary world is strange too. It is simply strange in a way that has been disciplined by decoherence into stability, predictability and familiar shape. Your coffee mug is not a rebuttal to quantum mechanics. It is a triumph of environmental monitoring. Your room is full of objects that feel definite because the surrounding world has continuously forced their delicate possibilities into robust, effectively classical states. Decoherence is the reason that quantum mystery does not hit you in the face every time you reach for the door handle. It is also the reason physicists have to work so hard when they want to glimpse that mystery clearly again, and once you see that, the next part of the story almost tells itself. If the environment is constantly silencing coherence and smoothing the microscopic world into something stable and classical, then the familiar world around us is not the opposite of quantum physics at all. It is what quantum physics looks like after decoherence has done its quiet work on a staggering scale. That is why the next question is no longer how a particle changes when you look at it, but why everything around you seems so calm, so certain, and so solid despite being built from ingredients that are anything but. By the time most of us first hear about quantum physics, we have already spent years trusting a very different kind of world. It is a world of tables that stay where they are, doors that remain either open or closed, cups that do not hover between being full and empty, and mornings that arrive with the same blunt certainty whether or not we feel ready for them. The everyday world looks solid, certain, and calm because nearly everything around us behaves in ways that fit the old classical script. Objects have locations, causes have effects, histories feel settled. A chair does not seem to occupy several positions at once. A spoon does not announce that it exists in a delicate superposition of the kitchen drawer and the sink. Yet the modern understanding of nature says that these ordinary objects are built from constituents governed by quantum rules. The puzzle, then, is not why quantum systems are strange. The puzzle is why the larger world usually is not visibly strange at all. The answer points back to decoherence, and to the way the environment relentlessly suppresses interference and helps produce the appearance of classical reality. This is one of the most important shifts in the whole subject. The everyday world is not separate from the quantum world. It is what the quantum world looks like once vast numbers of interactions have done their work. Decoherence studies how interference effects are suppressed by interactions between a system and its environment, and one of its major promises is to explain the emergence of classicality, meaning the ordinary world of localized objects and approximately predictable behavior that we actually inhabit. The Stanford Encyclopedia of Philosophy puts this at the center of the subject, asking whether the results of decoherence can explain the classical appearance of the everyday world, including both localization and familiar trajectories. That is the real bridge here. Calmness is not the absence of quantum mechanics. Calmness is quantum mechanics after the environment has repeatedly forced delicate possibilities into robust, effectively classical forms. If that sounds a bit severe, it is because the environment is severe. A microscopic system can preserve coherence only if it is protected from too much contact with the outside world. Large objects are never protected in that way. They're constantly bathed in light, bumped by surrounding air, warmed by thermal motion, vibrated by the surfaces supporting them, and entangled in 1,000 small exchanges with their surroundings. Information about them leaks everywhere. Their position, temperature, shape, and motion are continuously being recorded, not in a tidy notebook, but in the surrounding world itself. Photons scatter from them. Molecules collide with them. Sound waves nudge them. The environment does not merely surround large objects, it keeps score on them. That is why decoherence is so effective at larger scales. A big object is not left alone long enough for its quantum alternatives to remain visibly coherent in the way a carefully isolated microscopic system can. This means that what feels obvious to us is in fact the result of a tremendous amount of hidden physical bookkeeping. A chair appears to have one location because any superposition of very different locations would decohere almost instantly through interactions with its environment. A grain of dust looks like it follows a path instead of spreading into a visible quantum haze because the surrounding world is constantly monitoring it in a broad physical sense. The classical appearance of the world is not simply given for free, it is maintained, it is stabilized, it is enforced by the fact that large systems are deeply open to their surroundings. The Stanford Encyclopedia describes decoherence as highly relevant to explaining the emergence of the classical world, and that is precisely the point here. The reason your room looks settled is not that the quantum rules stopped applying, it is that those rules, applied to a system in contact with an environment, favour the rapid suppression of the interference effects that would make the room look overtly quantum. There is something almost comforting in that once you get used to it. The world is not calm because it is simple, it is calm because it is noisy. That sounds backwards at first, but only until you remember what kind of noise matters. Quantum coherence is delicate. Interference requires alternatives to remain phase-related in a precise way. The environment is exceptionally good at ruining that precision. So the very bustle of the world, the endless circulation of energy, radiation, collisions and thermal motion, is what helps make everyday objects appear stable and classical. The silence of ordinary certainty is achieved through the chatter of countless microscopic interactions. The weirdness is not missing, it is being drowned out. CERN says that surrounding interactions can quickly suppress interference through quantum decoherence. Once you recognize that, the stillness of the ordinary world begins to look less like the natural default and more like the visible outcome of a merciless filtering process. This also helps explain why we are so bad at intuiting quantum mechanics. Our senses did not evolve to detect coherence, they evolved to navigate a world where decoherence has already done nearly all the sorting before we arrive. By the time you see a cup on a table, the environment has already forced that object into a form stable enough to leave reliable visual traces. By the time you hear a sound, the air has already carried an effectively classical signal to your ear. By the time you judge where the door is, countless interactions have made that location robust enough for you to trust. Human perception is tuned to the aftermath, not the microscopic prelude. We live inside a reality that has already been rendered into dependable terms long before thought begins. That is one reason quantum physics feels so alien. It asks us to reason about the layer underneath the layer our brains were built to use. Another way to feel the point is to compare microscopic experiments with quantum technologies. In laboratories, researchers go to extraordinary lengths to isolate systems from the environment. They cool devices, they shield them from stray fields, they remove air, they reduce vibration, they control timing with absurd care. They do all this because coherence is precious and easy to lose. IBM notes that qubits are extremely sensitive to their environment and therefore prone to errors like decoherence and noise. That engineering fact is really just the everyday world making its usual demand. If you want to preserve quantum behavior, you must keep the rest of reality from intruding too quickly. If you do not, the environment will turn your elegant superposition into something effectively classical before you have time to use it. The calm certainty of ordinary objects is the same process seen from the opposite side. They look stable, because nothing has been done to protect them from becoming so. This is why the famous contrast between the quantum and classical worlds can be a little misleading if stated too sharply. It suggests that there are two different realities, one weird and one sensible. A better picture is that there is one underlying framework but different regimes of visibility. In tiny, protected, carefully engineered systems, the coherent quantum structure can remain visible long enough for interference, entanglement, and other delicate effects to matter. In large, warm, strongly coupled systems, that structure is rapidly dispersed into the environment, leaving behind the stable, local, classical behavior we recognize. The Stanford Encyclopedia presents decoherence as relevant precisely because it can display tantalizingly classical aspects at the level of components of the quantum description. That is not a retreat from quantum theory. It is quantum theory explaining why larger systems begin to look as though they obey a cleaner, older logic. It is also worth noticing that certainty in the everyday world is often approximate, not absolute. A ball rolls across the floor in a way that seems fully classical, but if you look closely enough, the deeper description still belongs to quantum mechanics. Classical behavior is often what emerges when the quantum details that could produce interference are no longer accessible. The world does not become fundamentally non-quantum at large scales. It becomes effectively classical for all practical purposes because decoherence is so overwhelming. This point matters because it prevents us from turning classicality into a myth of perfect certainty. The ordinary world is dependable enough for life, engineering, and memory. It is not a separate kingdom with new fundamental laws replacing the old ones. It is a robust approximation made possible by environmental interaction on a gigantic scale. That approximate character helps explain why some of the older mysteries linger. Decoherence goes a long way toward explaining why interference disappears and why certain states become stable enough to look classical, but it is often presented carefully, rather than triumphantly in foundational discussions. The Stanford Encyclopedia is explicit that decoherence is highly relevant to the measurement problem and to the emergence of the classical world, yet the relationship still needs interpretation rather than automatic closure. That means we should resist two temptations. One is to say decoherence solves nothing, the other is to say it solves everything. The more honest position is that decoherence explains a great deal about why the world looks the way it does, especially why coherent alternatives become so hard to observe in macroscopic systems. That already carries enormous weight in this story. You can see the practical force of that in the CERN antimatter work. The base collaboration kept a single trapped antiproton oscillating coherently between two spin states for 50 seconds only by suppressing magnetic field fluctuations and measurement interference. CERN was direct that preserving coherence is essential for controlling and tracking the evolution of such quantum systems. That phrase turns out to be the entire issue in miniature. If the world around the antiproton is allowed to push too hard, the coherence goes quiet. If researchers reduce those environmental disturbances enough, the coherence survives long enough to study. What is true for the trapped antiproton is true in a broader sense for all visible quantum weirdness. It is not absent from the larger world because nature disapproves of weirdness. It is absent because the larger world does not stop touching things. Once that sinks in, everyday reality begins to look almost theatrical in a different way. The table appears solid because the countless atoms and subatomic constituents beneath it are not being given the peace required to advertise their coherence. The mug seems certain because the surrounding world has effectively chosen and stabilized the properties that matter at that scale. The room seems calm because the environment has been doing a furious amount of unnoticed measuring, scattering, and correlating. In a sense, the world is full of outcomes because it is full of interactions. It is not waiting around to decide what it is. It is continually being rendered into stable form by the same physical processes that make genuine quantum isolation so difficult. That is why our experience feels so settled. Stability is not an accident. It is the visible face of relentless environmental entanglement and decoherence. This has a subtle emotional effect once you begin to live with it. The classical world stops looking like the boring version of reality and starts looking like a major achievement of the underlying physics. Ordinary objects are not dull because they are beneath quantum mechanics. They are remarkable because they are what large-scale quantum systems look like when coherence has been suppressed so thoroughly that localization and stability dominate. The Stanford Encyclopedia frames this in terms of the emergence of classicality, and emergence is the right word. The chair does not deny the quantum world. It emerges from it in a form disciplined by the environment. The same goes for your hands, your breathing, the walls around you, and every quietly dependable thing that lets daily life proceed without each morning becoming an experimental crisis. There is also a lesson here about why microscopic results from CERN and similar laboratories matter so much. Those experiments do not show us a different universe from the one we inhabit. They show us parts of the same universe under conditions where coherence and entanglement have not yet been erased beyond easy recovery. A trapped antiproton that keeps its coherence for nearly a minute is not exotic because it lives outside the laws that shape your kitchen. It is exotic because the experimental setup has managed to hold back the environmental pressure that usually makes the kitchen so reassuringly ordinary. When collider experiments reveal entanglement in top quarks, they are not opening a portal to a foreign reality. They are catching the familiar foundations before the classical mask has fully settled into place. So why does the everyday world look solid, certain, and calm? Because the alternatives that would make it look otherwise are almost never allowed to remain coherently visible. Because environmental interactions are everywhere and never sleep. Because the ordinary world is built from systems that have long since become inseparable from surrounding photons, fields, heat, vibrations, and matter. Because decoherence does not need permission to operate. And because the same theory that gives us entanglement, superposition, and quantum possibility also predicts that under the conditions of ordinary life, those features will be hidden beneath a durable classical surface. What feels obvious is therefore not the starting point of reality. It is the large-scale result of how reality has been interacting with itself all along. That is the quiet reversal at the heart of this whole subject. The familiar world is not familiar because it is more fundamental. It is familiar because the more delicate truths are harder to keep in view. We experience the settled aftermath, not the fragile possibility structure that lies underneath. Once you begin to see that, the dramatic headline about a particle that changes when you look at it starts to shrink into its proper size. The deeper story is larger and calmer than the headline ever was. It is about how certain conditions let quantum behavior remain visible, how other conditions bury it, and how experiments at CERN have learned to catch that behavior in systems where ordinary intuition would have expected only chaos. Which brings us naturally to the question we have been circling all along, namely what CERN actually found, and why the careful truth is much more important than the sensational version. So now we can finally answer the headline honestly, and in some ways the honest answer is more unsettling than the dramatic one. CERN did not announce the discovery of a brand new particle that literally reacts to a human gaze. No scientist at the Large Hadron Collider opened a detector, peered inside, and found a tiny object performing differently because it felt watched. What CERN actually found was more serious than that, and much more useful. It found new ways of showing that quantum systems can preserve strange relationships, shift between identities, and lose or keep delicate coherence depending on how they interact with the world around them. The real subject was never a particle with stage fright. The real subject was the role of interaction in deciding what kind of reality becomes visible. That is why the headline both fails and succeeds. It fails because it points you toward the wrong image. It suggests human attention as the key ingredient, and that is not what the CERN results showed. It succeeds because it hints that observation, in the physical sense of measurement and coupling, is not a trivial afterthought in quantum physics. The system you isolate is one thing. The system you probe, trap, collide, or let leak information into an apparatus is another. That difference is not a philosophical garnish. It is part of the physics itself. CERN's recent results made that point from several different directions at once, and taken together they do change the shape of the conversation. The first thing CERN actually found, in the sense most directly tied to your title, was not a mysterious new particle at all, but entanglement in an old one. In September 2024, CERN announced that the Atlas collaboration had observed quantum entanglement at the Large Hadron Collider for the first time between top quarks and top antiquarks at the highest energies yet explored for such a phenomenon. The CMS collaboration then confirmed the effect as well. CERN explained that if two particles are quantum entangled, the state of one is tied to the state of the other, and in this case the evidence came from the angular patterns of the particles into which the top quarks rapidly decayed. The top quark is the heaviest known fundamental particle, and because it decays before forming bound states with other quarks, its spin information can be inferred from its decay products. That allowed ATLAS and CMS to observe spin entanglement in a regime where such quantum effects had remained largely unexplored. Now, why does that change anything? Not because it proves that consciousness controls matter, not because it means particles whisper to one another across the detector. It changes things because it extends quantum entanglement into a domain of energy, violence, and experimental complexity, where many people instinctively expect only classical-looking wreckage. The Large Hadron Collider is not a gentle tabletop setup with carefully shepherded photons. It is a machine that smashes protons together at 13 tera-electron volts and sorts through torrents of debris. To find entanglement there means the quantum structure is not some delicate curiosity confined to neat little lab demonstrations. It remains meaningful and measurable in the very arena where we investigate the deepest ingredients of matter. CERN itself framed the result as opening a new perspective on quantum physics at high energies. That is one reason the truth matters more than the headline. The discovery was not smaller than the clickbait, it was bigger and more disciplined. The second thing CERN actually found was not a particle changing because of attention, but a particle whose very identity is already quantum mechanical before anyone asks the final question. In 2021, CERN reported that the LHCb collaboration had measured the tiny mass difference between two states called D1 and D2, which it described as manifestations of the quantum superposition of the D0 meson and its antiparticle. This mass difference controls the speed at which the D0 oscillates into anti-D0 and back. CERN explained the D0 in language that almost sounds like the sort of sentence a cautious public relations team ought to avoid, except that in this case, it is physically justified. The D0 particle can be itself and its antiparticle at once in a quantum superposition, and that superposition produces the two relevant states with slightly different masses. The collaboration measured that mass difference and crossed the 5 sigma threshold used to claim an observation in particle physics. That also changes everything, though in a quieter way. It changes how we imagine particle identity itself. In everyday thinking, a thing is itself and not its opposite. Matter is matter. Antimatter is antimatter. The D0 system reminds us that at the quantum level those neat labels can be part of a larger description, rather than final declarations. The meson is not just a tiny bead carrying one permanent label as it travels along. The physical states that govern its evolution are superposed combinations, and those combinations are what allow the oscillation to happen. CERN called the result a milestone in the study of how the D0 changes from matter into antimatter and back. It is difficult to overstate how conceptually rich that is. A particle does not have to be discovered yesterday to transform your picture of reality today. Sometimes the transformation comes from learning that a familiar particle was never obliged to fit your classical grammar in the first place, and the D0 story did not stop there. Back in 2019, CERN announced that LHCb had observed CP violation in D0 meson decays for the first time. That meant the collaboration had seen a matter-antimatter asymmetry in a system containing a charm quark, a new flavour in the very literal particle physics sense. CERN described CP violation as essential to understanding why matter dominates over antimatter in the present universe, while also stressing that the amount known so far in standard model interactions is too small to explain the full imbalance. This means the D0 meson is not only a lesson in superposition and oscillation, it is also a testing ground for one of the largest unanswered questions in physics: namely why the universe did not end in a grand mutual cancellation of matter and antimatter. If a particle can oscillate between matter and antimatter forms, and also show an asymmetry in how those forms decay, then the system becomes more than an oddity. It becomes a place where the deep history of the cosmos may have left a faint and measurable trace. The third thing CERN actually found was perhaps the closest to your title in emotional flavour, because it deals most directly with the fate of delicate quantum behaviour under observation and environmental disturbance. In July 2025, CERN announced that the base collaboration had kept a single trapped antiproton oscillating smoothly between two quantum spin states for almost a minute, creating what CERN called the first antimatter qubit. This was not a story about a particle reacting to a human glance. It was a story about preserving coherence by suppressing decoherence mechanisms. CERN said explicitly that interactions with the surrounding environment can quickly suppress interference effects through quantum decoherence, and that preserving coherence is essential for controlling and tracking the evolution of quantum systems such as the spin transitions of a single antiproton. The collaboration achieved a spin coherence time of 50 seconds after suppressing magnetic field fluctuations and measurement interference that had plagued earlier, incoherent techniques. This result changes everything in yet another sense. It changes the practical horizon of what can be done with antimatter in precision physics. CERN noted that the ability to perform coherent spectroscopy on a single antiproton opens the prospect of much more precise comparisons between matter and antimatter and substantially improved tests of nature's fundamental symmetries, especially charge parity time symmetry. In plainer terms, the result says that antimatter need not be studied only as something that annihilates on contact or exists as brief curiosity. It can be controlled with the language and methods of modern quantum science. But the philosophical importance is just as striking. Here the lesson is not that a particle changes when looked at, but that the world must be kept calm enough for the particle's quantum possibilities to survive at all. That is a very different sort of mystery. It shifts the focus from human attention to environmental pressure. What changes the system is not watchfulness in some mystical sense, but the physical fact that the surrounding world is usually far too noisy to let delicate superpositions breathe. So what did CERN actually find? It found that top quarks at the Large Hadron Collider can preserve entanglement in a measurable way at record energies. It found that the D0 meson is governed by superposed states that let it oscillate between matter and antimatter, and that this system also shows CP violation. It found that a single trapped antiproton can be held in coherent quantum motion long enough to become the first antimatter qubit. None of these are the same result, but together they tell a consistent story. The quantum world is not weird only when someone invents a dramatic metaphor for it. It is weird in its structure, in its correlations, in its symmetries, and in its fragility under interaction. CERN did not discover a particle that notices being watched. It helped reveal a reality in which the boundary between isolation and interaction is one of the main things deciding what can be seen at all. That is why the phrase changes "everything is not entirely overdone," provided we understand what kind of change is meant. These results do not mean your coffee mug will begin oscillating into anti-mug if you glance at it too hard. They do not mean the old physics was wrong in the everyday situations where classical ideas work perfectly well. They change everything at the level of understanding. They change the map. They remind us that the deeper description of reality is built not from fixed classical facts sitting quietly in advance, but from quantum states, entanglements, oscillations, symmetries, and interactions that only later settle into the robust outcomes our senses are tuned to trust. The calm world of ordinary life is not overturned by these discoveries. It is recontextualized. It begins to look like the large-scale appearance of something much more subtle. They also change the relation between foundational physics and practical experimentation. For a long time, some of the strangest questions in quantum theory were treated as if they belonged mainly to thought experiments, delicate optical tests or the philosophical side of the subject. CERN's recent work helps push those questions into the centre of frontier particle physics. Entanglement is not just for low-energy laboratory demonstrations. It can be studied in top quark pairs at the LHC. Coherent quantum control is not just for trapped ions or superconducting circuits. It can be extended to single antiprotons. Quantum mixtures of particle identity are not merely teaching tools. They're part of the real behaviour of mesons studied in collider data. That broadens the entire field. It means that the same machines built to uncover the deepest constituents of matter can also become laboratories for testing the fabric of quantum reality itself. There is a second sense in which these results change everything, and it is more personal, though still scientific. They force us to revise what we mean by explanation. In the classical imagination, to explain something is often to identify the hidden object, the hidden cause, the hidden mechanism already sitting there with one finished identity. In the quantum world, explanation often means identifying the state, the couplings, the symmetries, the possible measurement outcomes, and the routes by which coherence is preserved or destroyed. That is a quieter kind of explanation, less like unveiling a secret box, and more like understanding the rules of a very strict but very alien game. CERN's results reward that quieter style. They do not give us a magical particle with a memorable personality. They give us a set of systems in which nature's deeper grammar becomes visible if we are willing to follow it carefully enough. And perhaps that is the most satisfying correction to the original headline. The headline encourages you to imagine a particle that changes when you look. The truth encourages you to imagine that reality itself is structured by what can remain isolated, what becomes correlated, what leaks into the environment, and what a measurement setup is allowed to ask. That is a much more demanding thought. It asks less of our appetite for the dramatic and more of our patience. But in return, it offers something better than shock. It offers coherence between very different results. The top quark entanglement result says that joint quantum states remain meaningful, even in the violent environment of the collider. The D0 meson results say that particle identity itself can be governed by superposition and subtle asymmetry. The antimatter qubit result says that coherence can be protected long enough to turn antimatter into a controllable quantum system. These are not disconnected curiosities. They are different windows onto the same underlying lesson. Interaction is not a side issue. It is part of what reality is doing. There is one more reason the careful truth matters. Clickbait always threatens to make science feel silly once the exaggeration is removed, as though the real version must be less exciting than the headline. But here the opposite happens. Once you stop asking whether a particle notices human eyes, and start asking how quantum states survive, how they become entangled, how matter and antimatter blur into one another, and how environmental interaction suppresses or reveals those possibilities, the subject becomes richer rather than poorer. The science grows up. It stops being a trick and becomes a worldview problem. What sort of universe are we living in if definite facts emerge only after interactions that also erase part of the prior coherence? What sort of world is this if even the heaviest quark can be entangled at collider energies, if a meson can oscillate between matter and antimatter, and if a trapped antiproton can serve as an antimatter qubit? The real answers are not simpler than the headline. They are simply harder to phrase in one breath. So yes, CERN actually found something that changes everything, but not in the cheap way the headline first suggests. It found that the world at its most fundamental is organised around states, relations, symmetries, and interactions that do not map neatly onto the old picture of small solid things carrying fixed properties through empty space while we inspect them from a safe distance. That old picture still works wonderfully for buses, bread knives, and forgotten umbrellas. But deep underneath it, the story is stranger and more relational than it appears. CERN did not give us a particle that reacts to being watched. it gave us stronger evidence that reality itself depends at crucial moments on what can interact with what can stay coherent, and what the surrounding world is allowed to learn. And once you have said all that as carefully as possible, there is still a final quiet question waiting behind it. If the universe is built this way, if outcomes emerge through interaction, if the ordinary world is the settled surface of something deeper and stranger, then what exactly are we to make of reality itself? Not the headline reality, but the calmer one underneath. Not the universe as a sensational story, but the universe as a place where possibility, relation, and observation seem woven together more tightly than common sense ever expected. That is where the last part of this journey has been heading all along. And so we arrive at the point where the science becomes quiet enough that it starts to sound almost like philosophy, though it never stops being science. We began with a headline that seemed to promise something theatrical. Particle that changes when you look at it. By now that sentence has lost most of its cheap drama, but it has gained something better. It has become a doorway into a harder and more interesting idea, which is that the world at its deepest level may not be best understood as a collection of little objects carrying complete private identities all the time, entirely independent of what they interact with. Instead, the world may be built in a way that gives interaction a more central role than common sense first expects. That is not the same as saying reality is invented by human attention. It is not the same as saying nothing exists until someone stares at it over the rim of a coffee cup. CERN did not find that, and the broader physics does not require it. What the experiments and the theory suggest is something subtler. Quantum systems can remain in superposed states while suitably isolated. They can become entangled so that the pair is better described as a whole than as two separate little stories. They can lose delicate coherence when information about them leaks into the environment. CERN has reported each of those themes in real systems, from entangled top quarks at the Large Hadron Collider to D0 mesons that oscillate between matter and antimatter descriptions, and to trapped antiprotons whose coherent behavior survives only when decoherence is suppressed. Once you put those pieces together, the old picture of reality begins to feel slightly too blunt. It is not wrong in the ordinary realm where tables stand still and train times matter, and cups fall off counters in a perfectly discouraging way. But it may be incomplete as a description of what the world is doing underneath. The everyday picture says that things have properties, full stop. This chair is here. That lamp is there. The stone is hard. The window is shut. Quantum physics replies gently but firmly that this language works very well once decoherence has already done its work, once the environment has forced a stable classical face onto the system. But beneath that stable face, the situation can be more relational than that. What is possible depends on the state. What becomes definite depends on the interaction. What remains visible depends on how much of the system has been allowed to leak into the surrounding world. There is something almost unnerving about how ordinary that begins to sound once you live with it for long enough. After all, even in daily life, nothing is ever completely alone. Everything is touching something, exchanging something, heating something, reflecting something, disturbing something. Reality at our scale is one giant public square of interaction. We just rarely notice, because the interactions are so abundant and so familiar that they cease to look like events and start to look like the natural background of existence. But in the microscopic world, where coherence can survive long enough to matter, the difference between isolation and contact becomes visible in a way that forces us to rethink the old idea of a world made only of finished facts waiting to be read out. Perhaps that is why the experiments at CERN feel so important, even when they are not discovering a new particle in the flashy headline sense. They are showing in different ways that interaction is not a minor technical inconvenience added after the interesting part. It is part of the interesting part. In the top quark entanglement result, the point was not merely that two heavy particles existed and then decayed. The point was that their shared quantum state could be inferred from the correlated structure of the decay products. In the D0 meson results, the point was not merely that a particle changes label over time. The point was that the state itself is built from superposed combinations that make the classical labels matter and antimatter insufficient on their own. In the antiproton work, the point was not merely that a spin was measured. The point was that coherence had to be protected from environmental interaction long enough for the measurement to reveal something more subtle than mere noise. So the quiet mystery of reality is not that the world hides from us. It is that the world seems to reveal itself only through relationships. We do not get access to some bare thing untouched by circumstance. We get systems prepared in certain states, interacting with certain devices, embedded in certain environments, yielding certain records. That is not a defect in science. It is the shape of the subject. The world does not seem eager to present us with an inventory of absolute private properties, divorced from every context. Instead, it gives us outcomes that emerge through interaction and structures that are often best understood relationally. Now, one must be careful here, because this kind of language can become slippery very quickly. To say reality depends on interaction is not to say that nothing is real without us. It is not to say that the moon stops existing when clouds roll in, or when nobody is outside to see it. It is not to say that the universe waited billions of years in a state of existential suspense for human observers to arrive with notebooks. The stars lived and died long before our species learned to misinterpret quantum mechanics online. The better way to say it is this: what becomes definite, what becomes recordable, what remains coherently possible, and what is washed into classical stability are all deeply shaped by physical interaction. That is a more modest statement than the mystical one, and also a more profound one, because once you say it that way, the world begins to look less like a theatre full of isolated actors and more like a fabric of relations. A particle is not merely a tiny object with a tiny private diary. It may be a participant in a shared state. A measured property is not always a secret already sitting on a shelf waiting to be fetched. It may be an outcome produced through a specific interaction that extracts classical information from a quantum description. A classical object is not simply a non-quantum thing. It is what a quantum system looks like after the environment has relentlessly suppressed the interference that would have made its deeper strangeness easier to see. IBM describes measurement as the interface between quantum and classical information, and that phrase turns out to carry an entire worldview in disguise. The world we inhabit is full of interfaces. There is something humbling in that. Human beings prefer nouns. We like stable categories. We enjoy the feeling that a thing is simply what it is. Perhaps that is because our lives require such confidence. You do not want to negotiate with a staircase about whether it feels definite enough to use. You do not want a frying pan that takes a philosophical interest in superposition halfway through breakfast. The classical world is not merely comfortable, it is necessary for creatures like us. But physics keeps whispering that this comfort is achieved, not fundamental. The world looks settled because at large scales the environment is ceaselessly settling it. And then there is time, which we began with in your reference piece, and which has a way of sneaking into every deep subject whether invited or not. Interaction gives outcomes not only their definiteness, but their before and after. A measurement is an event. A decay is an event. An interference pattern building up on a screen is a history. Decoherence itself is time-soaked. It is not merely that a state exists and then is known. It is that the possibility structure evolves, interacts, leaks, stabilizes, and leaves a record. In that sense, the universe we experience is not only one that depends on interaction, it is one that depends on interaction unfolding. Reality is not laid before us all at once in a single manageable heap. It arrives through processes, and those processes are what the experiments are really catching. This is one reason I think the phrase quiet mystery suits the subject better than louder alternatives. The mystery is not flashy once you clear away the clickbait. It is steady. It sits there in the fact that quantum theory works with stunning precision while continuing to press on our ordinary assumptions about what a property is, what a system is, and what it means for something to become real as a recorded fact. The mystery is that nothing in the results from CERN forces us into nonsense, yet taken together they still make the old picture of the world feel a little too shallow. The experiments are not shouting that reality is an illusion. They are calmly indicating that reality is structured in ways our everyday language was never built to handle without strain. That strain is not a failure. In some ways, it is the best sign that we are near something genuine. Language evolved for hunting, sharing food, warning one another about rivers, promising to be home by a certain hour, and explaining why someone else was definitely supposed to buy bread. It was not designed for describing entangled top quarks, oscillating mesons, or the preservation of coherence in a trapped antiproton. Naturally, it creaks a little. Naturally, it reaches for metaphors. The trick is not to throw away the metaphors entirely, but to keep teaching them their limits. A particle does not change when you look at it because it has become self-conscious. A quantum system changes under measurement because measurement is a physical interaction through which possibilities are turned into outcomes and coherence is often lost in the process. That sentence is less dramatic, but it is much truer, and truth has a way of becoming more interesting the longer you sit with it. There are also larger philosophical paths branching from here, though one need not walk too far down them to feel the air change. Some people hear these ideas and lean toward a relational picture of the world, where properties are meaningful within interactions rather than as isolated absolutes. Others prefer to think in terms of information, as though physical reality is in some deep way bound up with what can be recorded and transmitted. Still others hold to more traditional interpretations in which the oddness lies not in reality itself, but in the limits of what can be jointly known or described. Science does not ask us to settle those arguments tonight, or perhaps ever. What it asks is that we respect the results, and the results suggest again and again that interaction is not peripheral. Maybe that is why the ordinary world feels newly interesting after spending time with these ideas. A room no longer looks like a collection of static things. It looks like the visible edge of endless hidden negotiations. Light from a lamp reaches the wall. The wall reflects it. Air carries heat from one corner to another. Your body exchanges energy with the chair beneath you. Every surface is in conversation with its surroundings, every object participating in a web of interaction so dense that the classical world appears stable almost by force. Calmness, which once looked simple, now looks like the outcome of an immense amount of suppressed possibility. And still, for all this, the scientific picture does not become bleak. If anything, it becomes more intimate. The universe is not made less real by being relational. It may be made more alive to description. It means that what exists is not merely a pile of independent pebbles, but a world of structured connections, evolving states, and records born from contact. Even certainty, in the ordinary sense, becomes something more precious. It is not free. It is earned through the way the world continuously settles itself into stable forms. A table is trustworthy not because reality beneath it is dull, but because reality beneath it has spent every moment making the table trustworthy. That, I think, is one of the gentlest lessons quantum physics offers, once you stop demanding that it either be magical or mechanical. It is neither. It is stranger, and calmer than both. It tells us that the world is not simply what it is in isolation, because isolation is rare and fragile. The world is what it becomes through interaction, what it preserves through coherence, what it loses through decoherence, and what it leaves behind in the form of records. CERN's recent results matter because they let us watch these themes in places of extraordinary precision and scale, not in theory alone, but in data. Not in mysticism, but in matter. So when the room grows quiet again, and the headline has finished trying to impress you, what remains is something more durable. A universe in which possibility is real enough to matter, Relation is deep enough to shape outcomes, and interaction is central enough that the line between what a system is and how it is asked about can no longer be treated as an afterthought. That is not a sensational conclusion, it is a patient one. The particle did not need to notice your gaze. Reality was already doing something far more interesting. It was becoming itself through contact. And perhaps that is the most restful version of the mystery. Not that the universe is unstable in some frightening way, but that it is continuously settling. Not that nothing is real, but that reality is richer than the blunt categories we first learned to trust. Not that observation creates the world from nothing, but that interaction helps decide what kind of world becomes visible. Somewhere beneath the stable surfaces of ordinary life, the deeper language of superposition, entanglement, and decoherence is still at work, quietly supporting the certainty we lean on every day. And once you know that, the calm of the everyday world does not feel smaller. It feels deeper, as though all around you the universe is keeping its balance one interaction at a time.